Okay, thank you very much. Okay, so basically the activities I would like to show in this talk have been carried out in our group in Napoli in collaboration with SIC, the digital company of superconducting quantum technologies, with Marco Arzeo and Oleg Motanov, and are within European projects funded by Quantera and Aerostats Pool. So it is well known that a Josephson junction is a dispatcherless nonlinear device, and these unique features, which translate into an harmonic potential, make the Josephson junction the fundamental element of superconducting electronics and of all superconducting qubits. And indeed, from the first experiments between the 80s and 90s up to now, there has been a remarkable progress in designing new circuits and in solving important issues in order to improve the coherence times of superconducting qubits. And therefore, superconducting circuits have emerged as leading candidates for scalable quantum processor architecture. And this slide, some of the most important characteristics are summarized. And in particular, superconducting qubits can be considered as artificial atoms, as with macroscopic size, and their energy spectra are governed by circuit elements such as capacitance and inductance, and therefore are highly tunable. Of course, there are still some important challenges to overcome in order to build a large-scale quantum computing. For instance, the coherence of superconducting qubits is strongly affected by the latency of microwave connections at room temperature, which we need to use to control and read out the qubit state, and DC flux bias lines, which we can use to tune the qubit frequency. In particular, DC flux bias lines allow for fast gate operations, but make the superconducting qubit more sensitive to flux noise. And therefore, new routes, new solutions are needed in order to facilitate the scalability, the scaling up of the number of superconducting qubits. And the approach we are trying to pursue in collaboration with SIC is based on a hybrid classical quantum scheme. So basically, this approach is based on the development of integrated devices based on superconducting control, digital control electronics in a multi-chip module configuration. So within this approach, the idea is that both qubit control and readout can be performed in situ at the full stage of the experiment by using digital pulses and flux biases provided by the superconducting classical electronics. So this is a sketch, a typical sketch of a multi-chip module where the qubit array is above the superconducting classical circuits, and indium bumps provide the galvanic connections between the two chips. Therefore, instead of waveforms from room temp of microwave waveforms from room temperature electronics via dedicated coaxial lines for each superconducting qubit. The idea is that we can perform a qubit control and readout in close proximity to the quantum chip without the use of additional cables. So in the next slides, I'm going to show an example of a device for qubit readout, which is fully compatible with this kind of classical quantum architecture. So basically, the readout technique for the measurements of single qubits and two qubit gates is based on the heterodyne technique, which consists in sending a weak microwave signal to a linear resonator, superconducting resonator, which is dispersively coupled to superconducting qubit, a transmon for instance, and the output signal, which is transmitted across the resonator or reflected by the resonator, will bring the information about the qubit state. So in the last year, we have developed this new device, the Josephson digital phase detector, which is able to perform a phase detection of a weak coherent microwave tone. And this device is based on two RF squids, which share an inductive load in the middle, this inductance in the central part of the device. And this configuration allows to increase the number of degrees of freedoms in terms of fluxes in order to manipulate the Josephson energy, the potential energy of the device. This is the expression of the potential energy, where phi 0 is the flux quantum, phi plus and phi minus are the sum and difference of the two fluxes, phi 1 and phi 2 of the two RF squids. Basically, phi plus can be used to modify the potential shape, while phi minus can be used to provide a controller tilt. And finally, the phase phi is the dynamical variable and represents the phase drop across the center inductance. So in the symmetric case and for large value of the beta factor, the potential energy may have a single well or a double well minima. And this tunability allows us to perform a phase detection scheme, which I'm going to show in this slide by using PSCAN2 simulations. So PSCAN2 is a common software that we use to simulate the dynamical behavior of superconducting circuits. So in the first step, there is no external flux which is applied, and therefore the phase particle is confined to one potential well. Then we apply a phi 0/4 pulse. In this way, the potential energy becomes harmonic. In the third step, the signal that we want to detect will interact with the Josephson digital phase detector, and therefore the phase particle will start an harmonic motion with amplitude and phase which depend on the signal that we want to detect. In the last step, if we apply again a phi 0/4 pulse, the potential well will become a double well potential, and the phase particle will fall in the left or right side, depending on the value of the displacement theta, so on the value of the phase of the signal that we want to detect. And since the phase is proportional to the current passing through the central inductance, we can digitalize the output by measuring the sign of the current passing through this inductance. And therefore, we can obtain the information on the qubit state if we apply this to a superconducting qubit. So in the last few months, strong efforts have been dedicated to design the device by using numerical and electromagnetic simulations in order to have a set of parameters for the fabrication process. So the fabrication has been made by SICK in the US, and the measurements, and we have measured the device. Basically, the Josephson digital phase detector can be considered as a device with a variable inductance, and therefore the system composed by the linear resonator and the Josephson digital phase detector has a resonance frequency which depends on the value of the inductance of the Josephson digital phase detector, which depends on the external flux. And therefore, preliminary measurements reported in this slide confirm the functioning principle of this device, since we are able to modify the potential energy in the right way, and we are able to trap the phase particle in the desired potential well depending on the measurement protocol that we choose. And therefore, since the functioning principle has been demonstrated, the next step will be to couple this device to a superconducting qubit, to a transmon for instance, to perform qubit readout in close proximity to the device. Moreover, since the characteristic frequencies of the Josephson digital phase detector can be designed to be far away from the frequencies of the qubit, we expect also to reduce back action in this case. So this is an example of how the flexibility of joystick devices can provide new solutions in the field. Other solutions come from the continuous progress in material science and nanotechnology, which in the last 10 years have led to the realization of novel types of hybrid joystick devices with barriers composed by semiconductor nanowires, graphene sheets, ferromagnetic layers, and so on, with the idea to combine the properties of different materials. And in these devices, Josephson coupling is crucial in order to understand and characterize interface phenomena which can bring new or better functionalities also in the field of superconducting qubits. And therefore, it is quite important to distinguish the different dissipation sources in these unconventional devices and the measurements of critical current fluctuations, the switching current distributions, along with the temperature behavior of the width of the switching histograms, provide a direct technique, a direct tool to distinguish different dissipation processes and to reconstruct the electrodynamics of these devices. So in particular, Josephson coupling between superconducting and ferromagnetic layers is driving new fundamental effects, such as the possibility to switch the ground state of Josephson junctions from 0 to pi, the 0 to pi transition, the existence of a doubly degenerate ground state plus minus phi, the so-called phi Josephson junctions, the possibility to carry spin triplet supercurrents in presence of magnetic inhomogeneities, and for instance the presence of a magnetic hysteresis for the critical current as a function of magnetic field, and therefore magnetic hysteresis for the Josephson energy of the junction. At the same time, so I'm sorry for this slide, but at the same time, ferromagnetic Josephson junctions have been used in quantum circuits only as passive elements, as pi-phase shifters, since the higher level of dissipations due to the use of more standard metallic ferromagnetic barriers induce lower coherence times. On the other hand, in the last years, tunnel ferromagnetic Josephson junctions have been realized and show a series of very interesting phenomena. So for tunnel ferromagnetic junctions, we mean Josephson junctions with a ferromagnetic insulator barrier, such as gadolinium nitride in spin filter junctions realized by the group of Mark Blameyer in Cambridge, or junctions with a multilayer structures, for instance, SI-SFS junctions, in which the barrier is composed by both an aluminum oxide tunnel barrier and a more standard ferromagnetic layer, which is permalloy, palladium iron, holmium, and so on. So, as I mentioned before, in the case of pure metallic ferromagnetic junctions, the IV characteristics are non-hysteretic with low values of the ICRM product, and the junction fall in the over-damped regime. While if we consider tunnel ferromagnetic Josephson junctions, we have current voltage characteristics with hysteresis larger than 90%, under-damped regime, and high values of the ICRM product up to a few millivolt. Moreover, in the case of spin filter Josephson junctions, we have found strong features of unconventional superconductivity in terms of the temperature behavior of the critical current. In particular, we have observed a progressive deviation from the standard Ambergauer-Baratoff regime when increasing the barrier thickness. And in particular, in the highly spin polarized regime, we have found this non-monotonic behavior, this incipient 0 to pi transition. And therefore, we are able to explain these results only if we assume a non-uniform exchange field in the barrier, which is a strong ingredient of the spin triplet transport. In order to achieve a better picture, better fit of the data, we have used a macroscopic approach based on a tight binding Bogoliubov Hamiltonian. And this way we are able to fit the experimental curve in the whole temperature range and to determine a posteriori the current phase relation at finite temperature and also spin singlet and triplet correlation functions. And therefore it turns out that this extended plateau in the temperature behavior of the critical current is a benchmark for the coexistence of spin singlet and triplet transport in these devices. Moreover, these junctions can be used in quantum circuits. First of all, because macroscopic quantum tunneling has been demonstrated a few years ago by measuring the switching current distributions as a function of temperature, and we have found a transition from the thermal activation to the macroscopic quantum tunneling regime. And this is the first evidence of macroscopic quantum phenomena in ferromagnetic junctions, and therefore we may use these devices as active elements in a quantum circuit. Another fundamental part of the AV characteristic is given by the subgap branch. Indeed, this part of the AV characteristic is related to quasi-particles dissipation and provides information about the electrodynamic parameters such as junction quality factor and subgap resistance, capacitance associated to the barrier. So if we want to place the junction in a more complex circuit or to couple it to a cavity, to a superconducting resonator, the knowledge of the electrodynamic parameters and how they scale as a function of junction geometry is another fundamental step. And therefore in this work we used the tunnel junction microscopic model to fit the subgap branch. We have found values of the subgap resistance and junction quality factor which are 2-3 orders of magnitude higher than those commonly found in pure metallic ferromagnetic junctions, thus supporting the possible use of these devices in a quantum circuit. So basically, why we want to use this device in a quantum circuit? Because we may exploit the hysteretic character of the ferromagnet in order to manipulate, to tune the qubit in a different way, in particular by using magnetic field pulses. Indeed, if we use magnetic field pulses, we can move along the magnetic field pattern and measure different values of the critical current for the same value magnetic field. So apart from the possible use of these devices in superconducting electronics and as cryogenic memories, it turns out that the critical current and therefore the Josephson energy can be modified if we apply pulses. So while in a standard transmon qubit we have this is squared with 2 Josephson junctions which is inductively coupled to a DC flux bias line, and therefore the Josephson energy and therefore the qubit frequency has to be tuned by a static magnetic field which has to be applied during all the qubit operations. The idea is that we can replace the tunnel junction in the squid by using a tunnel ferromagnetic Josephson junction in such a way that the Josephson energy and the qubit frequency can be manipulated by using magnetic field pulses before all the qubit operations. And therefore we expect that this configuration may be helpful in reducing the flux noise. And moreover, this kind of configuration is fully compatible with the architecture based on superconducting classical electronics, which has been shown in the first part of the talk. Moreover, first simulations of this circuit we call ferrotransmon, so ferromagnetic transmon. First simulations of this device coupled to a linear resonator fully support the feasibility of this qubit. Also because we may tune the qubit frequency by using minor loops of the ferromagnet, so by using small values of the magnetic field pulses without affecting the properties of the superconducting electrons. And moreover, the fact that we can couple the superconducting junctions, the ferromagnetic junctions, to a linear resonator, to a microwave linear resonator, can be helpful also in studying some important properties of ferromagnetic junctions, for instance, the noise features of these devices, since the superconducting qubit can be considered as a very powerful sensor. In particular, in this work, we also show how the measurements of relaxations and dephasing processes, so the measurements of T1 and T2 in the superconducting qubit, allow us to estimate magnetization fluctuations and standard flux noise, and the comparison between this noise source will give us the chance to optimize the qubit design. And finally, in this very recent work, we have reported on the realization and fabrication, on the realization and characterization of tunnel ferromagnetic Josephson junctions with aluminum electrodes. So these are the first Josephson junctions, first ferromagnetic Josephson junctions with aluminum electrodes. And here the important result is that we are able to combine the typical transmol properties of tunnel aluminum junctions with the ferromagnetic behavior, the hysteretic behavior of the magnetic field path. This is evident also from the fact that we measure the same values and the same shape of the subgap branch in presence and in absence of the ferromagnetic interlayer. This can be explained if we consider that the behavior of SI-SFS junctions strongly depend on the thickness of the superconducting interlayer and on the thickness of the ferromagnetic layer. In particular, if the thickness of the superconducting interlayer is large enough, this device can be considered as a series of a tunnel SIS junction and a ferromagnetic SFS junctions, where the transport properties are regulated by the tunnel junction, which has a lower critical current. And this is an important result because if we want to realize a ferrotransmon, so a qubit with a ferromagnetic material, we can use the same fabrication process of a standard transmon, a standard aluminum transmon, and deposit the ferromagnetic layer in a second step without affecting the properties of the tunnel barrier and of the junctions employed in the quantum circuits. Moreover, this kind of technology is also compatible with a large variety of ferromagnetic materials, and therefore we can, in principle, realize ad hoc switchable devices, ad hoc in the sense that we can use the ferromagnetic material which is more suitable in terms of coercive field, saturation field, switching times for the magnetization of the ferromagnet. So there is a large flexibility. So in conclusions, our activities on the study of superconducting of quantum circuits mainly follow two directions. The first one is based on the possibility to use the flexibility of Josephson devices to address the scalability of a multi-qubit architecture by using this kind of classical quantum hybrid solution in which superconducting control devices are integrated with the quantum chip. And the second direction is based on the material science and nanotechnology notions in order to realize hybrid Josephson devices going beyond the pure aluminum technology, but with enhanced functionalities. And in this sense, tunnel ferromagnetic Josephson junctions seem to be very promising. And that's all. I would like to thank you for the attention.
Thank you. We have short time for short questions, please.
Yeah, so thanks for a very nice presentation. Let's say you show now the added value of using this, let's say, these ferromagnetic junctions, no? And this is clear to me. But can you also tell me a bit more about the negative side? Let's say if you go to T1 and you go in full design, isn't there an expectation that your lifetime of the qubit will drastically reduce?
Yeah, I mean, this is something that we have to test, of course. We don't have the first prototype of the ferrotransmit, but in principle, the fact that we are able to realize good devices, I mean, that the performance of the junctions with and without the ferromagnetic layers are almost the same, this is a strong result. And concerning the characteristic times, in principle, the fact that the junction work as a series of two junctions in which the ferromagnetic has a very large critical current can be helpful in this sense. This is something that we have to test, and in principle, there are many sources of noise that we have to address, and for sure we have to start from the magnetization fluctuations, but the use of a metallic layer, for instance, can be good in reducing the two-level system noise due to the electric barrier. So there are also some hope of, some better functionalities.
Okay, thank you. I'm afraid we have no time for further questions, but we have time in order to provide you an official certificate.
Thank you. Thank you very much.
Thank you very much.
Okay, don't use these. Yeah, up and down. Okay. Yeah. It's coming. So good morning, everyone. I would like to start by thanking the organizers, basically the Germans here, for giving me the chance to present some of our results. And I will be talking, as announced by the chairman, about the modification of multi-terminal superconducting weak links. So we'll change a bit of a topic. And this subject is actually it's not changed in the slide. I can start dancing if you want to entertain you. No. Laser works nice. You adapt to my time, right? I will skip the last slide, don't worry. No. I can talk for an hour about this slide, but so I'm pointing you. Can shoot you with the laser as well. No, nothing happened. Okay, it's not the speaker. That's already a good thing. We can start clapping and we gain some time. If you change with the finger, it works well as well. There is no, I say change the slide and you just. I'm trying as hard as I can, yeah. Nix. Nothing happened. about the finger on the keyboard? It's like my work. Yeah. I changed the speaker as well. Oh, a no pointer. Okay, I will use my hands. So, and now it works. Okay, let's go again. Yeah, no problem. Yeah, let me see. Yeah, it looks like going in the good direction. Very good. All right. So let me start by thanking the collaborators. This project we were running for 6 years already, so many people were collected on the way who help us to develop this technique I'm going to talk about. And mainly I would like to thanks to Professor Van de Wondel and his group here, who help us to also develop this at the beginning. And let's go to the point. So I've been talking about electromigration. So something for those who know very well, there is no need for introduction. Here I'm just say a few words. So the idea is very simple. You have a metal, you apply a high current to the metal or a high electric field, and then you're able to move atoms with that high current. That can be either because your electrons are producing a wind which actually push out the atoms from the side, or it could be that actually the electric field is so big that the ions in the lattice can move away. So and that's what basically we do to modify the properties of superconductors. The first question you might wonder is why we don't see this effect in daily life, and that happens because if you go to your household appliances, basically you just apply a small current density and you reach already the melting, above the melting temperature, and then you don't see electromigration. You just should hit your system and you melt it, and that's it. So in order to reach this electromigration regime, you had to go to small devices. So in that case, heat evacuation is very efficient, and then you can go much higher in current and actually never reaching the melting, but start moving atoms before you reach the melting. Now, that's the regime we are working on. So we work with the small devices to be able to get to high current densities. So we have done in the past several applications that, though basically you just make a constriction of your sample, you heat up, and then you start moving atoms and you change the properties. And then so we have like generated gaps, for example, in ferromagnets and conductors, and we have also tuned the properties of superconducting qubits, in this case niobium or aluminum. It's a sort of a reversible process. You can, in this case, in aluminum, we just move atoms and increase the resistance, and then invert the current direction and put them back again in the same place, and remove it again and put them back and remove it, and we do that thousands and thousands of times, and it's nicely reproducible. So you can do even a sort of a memory device with this system. So what I'm going to talk today is more about multi-terminal device. So far I show you only the case of two-terminal devices, and I show you the case of single atomic element devices. I'm going to show you today multi-terminal and what happens when you have several atoms in the system. So multi-terminals has been, it's becoming sort of fashionable today. There are many, many applications. You see more than two contacts in a conductor or superconductor. So some examples here is this Itron device. You can control the current by applying voltages to different branches, or injection of quasi-particles in squids to modulate the properties, or more recently, 3 junctions who are able to somehow tune the properties depending on where the electrons are coming from different junctions, and showing and exhibiting some even entanglement effects on that. So as you might see, all this requires quite some complicated nanofabrication processing, particularly in this case of you see multi-layers with 2D electron gases and stuff like that. So I'm going to show you that we can do that, perhaps easier, by just using electromigration. So I'm going to go for this example. We just take 3 junctions. We apply current from plus to minus, so high potential, electrical potential to lower, and then we have half of the current going in these 2 leads, and most of the current concentrated at this spot, and then we can locally modify the properties on that point. That's basically the idea. So let's start from this junction here. This is an aluminum 3 junctions you see over here. We apply the current from these upper 2 contacts. We are, on the same equipotential and towards this one. So basically, we are going to pass mainly the higher current density is going to be there. So if you simulate it, you see that you heat up only locally over there. And the idea is to see whether we can modify the properties over there. So we measure then the resistance, for example, this is junction 1, we call it, 2 and 3, and then we measure the voltage between 1 and 3, and that's what we get, the resistance 1, 3, and then we just apply current. So this is just resistance goes up because it's sure heating, and eventually you start to modify your material, become very, very vertical, and you can actually have to be careful to not burn it out. So this is the result. So we just measured afterwards. Once we have modified, we apply a small current. For example, if you want to measure 1, 2 between these 2 contacts, you measure resistance 1 and resistance 2. So you measure resistance 1 and 2. You can measure between this and this. You have 1 and 3, or you can measure between 2 and 3, between this contact and this contact, and you have 2 and 3. And they are, both of them are entangled in one measurement. But this is a linear system. So if you just consider resistance J, you have just the linear addition. So basically you have 3 data with 3 linear equations. So you can deconvolve this or solve the problem and isolate each of them. And that shows, for example, in this particular case, R1, R2 is very similar in the normal state. R3 is a bit higher because this is a bit narrower. So this is expected, no problem at all. So now we can start modifying. So first thing we do is we apply current between 1 and 3 towards 2, so we heat up only that part of the system. So what you have before is in blue for each of the resistance, each of the junctions, and you see after electromigrating this part, is only that one we modify, the others do not modify at all. It's so very, very target description. So you can even try to measure the critical current between 1 and 2, so you go through that part, you modify, you create a junction, and therefore the critical current is reduced and now exhibits Fraunhofer oscillations, which corresponds well to junctions. If you measure between 1 and 3, you never modify anything between 1 and 3, and clearly nothing happens. Before and after is the same. If you go between 2 and 3, you get the same oscillations. So you can go further and say, well, I modified already 2, and now I want to modify 1. So I want to modify that one without touching 2 and 3, and this is exactly what happens. So before is the last state here, and after, you see, we just modify this one, go up in resistance, we modify that junction. Nothing happened in 2, nothing happened in 3, and once again, same behavior. And we can do it now. We want to modify 3 and don't touch the other 2. It's exactly the same. And you can go on for as many, ways or times or iterations you want. So if you want to see what's going on in the sample, at the end, this is AFM images showing that basically we're, in this case, trying to modify the second junction here, and then you see how you start to build up a bit of material over there. This is a very, very, how to say, aggressive electromigration. This is really are pushing atoms out of the place, and as you can see in the AFM. Now I'm going to show you what happened if we go for a mild electromigration, very, very tiny amount of current, but enough to modify this. So in this research, actually is unpublished, we try to, first of all, address the influence of the geometry for mild electromigration. So this is our device. So we apply current, let's say, between this and this is the same equipotential, and we go to this part, and so we modify that junction over there. And then we change this angle of the junction from 90, 80, 70, and we'll show how electromigration propagates depending on the geometry of your device, okay? So I'll go very quickly on the procedure. In this case, we apply current pulses, and then we measure after the current pulse. Let's say once you have modified your system with high current, and at the pulse as well, when you have the Joule heating full power. So unfortunately, the colors are not very well chosen here. So actually, when you measure in the blue is the red, and when you measure in the red is the blue. It was too simple, so I tried to confuse a little bit. So look at the red. I think is the most interesting one, which is, don't forget that the blue. Okay. So the red is measure the resistance after you modify the junction. So it should be, if you don't modify, it should be a constant curve. So what you observe is basically at the beginning you improve the resistance. The system becomes better, and that has to do probably with, I mean, you might imagine releasing of stress on the substrate or some degassing or something. So we try to go above that and try to go above the initial resistance, but not more than 10%. So we just modify a little bit each of the junctions I show you in this case, okay? And then we take a picture for that, and this is what you see in the scanning electron microscope using the Eberhard-only detector, C2, and you barely see anything, actually. You did not modify, you had impression in the SAM, your junction. But if you look at the in-lens detector, you clearly see that there is a whiter part, let's say, coming from the part you modified, okay? And that looks like you increase the yield of electrons coming from the sample, okay? And in order to tackle that, we say, well, if it's that, probably we reduce the work function on the sample, okay? So we'll try to do some Kelvin probe microscopy, and this is indeed the case. We see that the work function has decreased exactly. But what is interesting is now we are able to control with the geometry of the sample the extension of how much you modify. Okay, so depending on the angle of you can change that. So you might have a good junction here and not a very long junctions there or something like that. So that's just to show a bit of control. The question is why the work function is decreased. They have been, I mean, can go on discussion about that. There have been a couple of works showing that it's always the case if you heat up a little bit the niobium, you have some fissorption of oxygen and carbon, and that tends to, let's say, reduce the work function in the sample. Okay. So we did some quick simulations where we take into account the heating produced by the current, the heat evacuation in the sample itself. We also take into account the heat evacuations through the substrate. By choosing the proper parameters, we are able to fit for each of the junctions the resistance measured during the pulse, which contains the Joule heating. That's the important part. And with that, we can model actually the temperature distribution in our sample and predict the extension. And we can even say what temperature we stop modifying the niobium. And this is about 430 Kelvin, which seems to be the point where diffusion of oxygen happens in these structures. Okay, but we go further inside there. So this is the 400 is just the border. If you go to the middle, you are about 570 or something like that. This is roughly estimations from the simulations. Okay, so now I change gears here. I'm going to change a bit of a topic. We'll see, so far we have seen how we can modify a single elemental material. In that case was niobium. I'm going to go now to the case we have a very complex material, several atoms. We wonder which atom are we going to move with the current. Okay, so for that I took a complex superconducting material, YBCO, which is, as you might see, full of different atoms. And the question is, if I apply a high current, which of all these atoms I'm going to move? Okay, so if you go back to the literature, you actually realize that the current in these systems goes through what is these copper-oxygen planes, and also through the copper-oxygen chains, unidimensional. And actually, most of the current, I mean, these guys back in the 90s, they measure single crystals, so there are no twinnings, untwinned single crystals, and they measure in direction of only the change can carry the current, or only the planes can carry current, or in the direction B, where both the change and the planes can carry current. And out of these measurements, they conclude that 40% of the current goes through the planes and 60% goes to the chains. And the chains are interesting because that means that you might have a high current density here, and sorry, I was a bit too fast. Most of the current goes through this one, and this oxygen you see over there, it can easily jump out and locate it in between these two coppers. Okay, that's the idea we have in mind, and that's the thing we're trying to move. So, and this is interesting because if you are only able to move one atom, the oxygen, you are able to change the distribution of oxygen in the system, and by doing that, is well known that you can change the whole doping in the system, and then you can actually scan the whole phase diagram of this system by just using current. Okay, you don't need to do several samples with different dopings. You just apply current and change the oxygen, and that was a bit the idea. So quickly done, this is our sample, and the sample, it has multi-terminals, so this is an important point. So we have a central bridge which is narrower, that's the one that is going to be affected the most, and then we have two bridges at the side, and then we can actually monitor each of them to see in which direction we are pushing the atoms, okay? I was confused with that. So let's see what happens. So we have, first of all, we measure the critical temperature as a function of how many times we try to move the oxygen atoms, so what we call electromigration run. So this part of the bridge in red to the left is what we call measure 1, B1, B2 is here. The central bridge is 2, 3, and the left is 3, 4. So the current is going in this direction, okay, from right to left. So we are pushing oxygen vacancies towards the left side, okay. So, and if you look at the how the voltage changes, so you see that the blue part is basically not changing much, and 1 and 2 and 2 and 3 are changing substantially. And this is because you are actually moving oxygen from here, oxygen vacancy from here to here, and then you are depleting the oxygen here, and then superconducting properties becomes weaker, and that's why TC goes down, okay? So this is underdope YVCO, and this is a bit overdope. So I don't know why the slides are changing long, but so here is, we do the same device, but then we measure the whole voltage. Now the region which is colored over there, and then we see that actually between 3 and 7, this one, we see that the carrier density mainly has a tendency to increase, while in this case it has a tendency to decrease the system. So that also proves that we are moving oxygen vacancies to this side and oxygens to the other side. And we can even, from this data, put it on the phase boundary, and it goes more or less okay with what is published in the literature, so showing that it's a good way to do it. So this is showing also that how we are moving these oxygens. To check that, we use Raman measurements. So the idea is like more you have the oxygen vacancies on the system, higher is this delta, and when delta is higher, the z-axis of the unit cells become longer, extended, and then the phonon modes become softer, okay, and the frequency goes down. So the idea is to check the phonon modes, which are pointed out with the blue arrows here, and try to see how they change as a function of position. So we check the Raman in these spots that you see green along the bridge. We take the pristine sample, and we see this is sort of monolithic. This sample is constant, so we can even get how many oxygens we have over there. And then we electromigrate once, and you see that how in the central region you deplete that. So here is the frequency of the Raman mode that you translate to the oxygen content. So you see how the oxygen content go down in, and if you continue electromigration, you see how these propagate to the left. Okay, so you have less and less oxygens coming to this side of the sample. So basically we are once again pushing oxygen vacancies here, oxygens to the other side. So we can even do, you know, back and forth current. So these are the 3 bridges. Color code is here. 1, 2 is red, central is green, and on the right 3, 4 is blue. So we apply current, let's say positive current, which means flowing from right to left, and then we apply 5.8 milliamps, and you see on 1, 2 the resistance goes up. That means oxygen vacancies are arriving, while the green goes down and the blue goes down. Means oxygens are arriving on the other side. So we are changing vacancy here, oxygen there, and yeah, and then we just apply current constant, and here we suddenly change to minus. So we invert the current direction, and you see how you now bring, so resistance goes down, so we bring to this side oxygens, and this one increases and then decreases. I'll explain in a second. This one increases, so we are bringing oxygen vacancies here, and what you see going up and down is because it's a passage of oxygen vacancies and oxygen atoms counterflowing one direction to the other, okay? And then we reverse the current again, and then, yeah, well, it's the same story. As you might see, it's very reproducible. So we can bring oxygens from one point to the other, back and forth, and that's all, okay? And what you see in the middle is just the passage of these oxygen atoms. So we can go further, and we can image that, because when you have a depletion of oxygen in the YVCO, reflectivity goes up. So if you just look at the optical microscope, you see it brighter. And this is exactly what we see. So this is initial stage, and then we push oxygen vacancies to this side, and what you see like brighter is where oxygen is missing, okay? And then we put it to the other side, and yeah, and back and forth. You don't see it much here. I have a nice movie to show you. You have to take differential images, and then you see how this is changing as a function of time, basically. And these waves sometimes comes because of the contacts, because they produce current crowding at the contacts, and the current density is not homogeneous. So we have even simulated these results recently, and I guess I'm going to close in the next 2 slides. Quickly done. I wanted to show you that we went beyond YVCO. We try LSMO, which is a ferromagnetic material, but it's a very peculiar manganite system where you only have, let's say, good conductivity if you have high magnetization, okay? So this is double exchange mechanism. I will not go through the details, but the only way you can get this manganite like a decent conductor is to go to low temperatures. So the only way to do this effect is to go to 100 kelvins, for example, and then we see for the first time also how we move the vacancies over there. Another feature we observe in this case is this is happening just before you have the dielectric breakdown, and then you generate cracks in your STO substrate. I will not go into the detail that you can also nicely visualize optically, but I think it's a bit too much for this talk. So I just put my conclusions. I think we have an accessible and powerful technique for modulation of your superconducting devices. And you can do many things with that, from gaps to cleaning your samples, and you know, fabricating memristors, nano gap, point contacts. It might be reversible depending on the system, and yeah, you know, it's up to you to find the application as well. Thank you for your attention. Yes.
But the excess oxygen doesn't make additional charge transfer. So it's rather defects inducing this oxygen edge side should show up somewhere in the transport properties. Maybe reduce ETC.
Yeah, that's, I mean, getting over dope is difficult. So on that side, we just see a very mild increase of TC. No, we didn't see much more than that. We didn't see any decrease of TC. What we believe is like this process, if you follow it for a longer time, this is just a little bit, but you will see that there is a tendency on both sides to go up actually. So I think we are also losing oxygen from the system, you know, so it's, but I don't think we really get overdope much, but probably you have the effects indeed.
Okay, thanks.
Does we want another question on this side?
Thank you for this presentation. My question is about this reversibility process actually. You have showed us data with the resistance. Do you think you can also reverse the process where you showed the niobium junction formation, for example, appearing and reappearing of this Fraunhofer pattern?
Yeah, that's a very good question. Look, we try that, and you see an improvement when you inverse the current, so definitely you heal a little bit, but it's very fragile. We end up, you have to control it very carefully. I don't know why, but the sample end up exploding at a certain moment.
As
So
a follow-up question, I'm so sorry. So did you do elemental analysis of those junctions? For example, XPS or EDS analysis to see that this is not actually oxidization, but a migration? Because you're heating the niobium up?
Yeah, we have tried, we don't have any conclusive information. We have tried a bit of atom probe, we have tried, I think, also XDS, but don't have a clear conclusion. The point is, there are small, really small junctions, you know, and sometimes for the techniques we have, it's not that
I see, thank you.
big to get the data. Yeah.
Perhaps that's the last one.
Very good question. How thick is your niobium?
Niobium 50 nanometers. 50, yes, yes, yes. I think I can take one more, eh?
Oh, yes, please.
Just from the point of view of electronics, so can you think about reconfigurable kind of electronics using your framework?
Oh, yeah, perhaps, why not? I never thought about that.
I mean, it's like, it seems to me that you can somehow modify the material properties
Right.
in quite reversible way. So perhaps you can think in the direction of programmable matter in the sense of...
Yeah, in some sense, what I show like a memristor was in that direction, you know, that the fact that we could change the resistance of the device. And we did it for several thousand times, but it's tricky. Eventually, it's always irreversible, irreversible, you know, at the end of the day. You can do it for 1,000 times, but perhaps not for a million times.
Perhaps you don't need 100 times to change.
Yeah, okay, yeah. No, but that's a good direction, yes.
Maybe you can, as the very last one,
Yeah, sure. All the analysis that you did, was that in situ, like the SEM imaging where you showed that the work function and the like Kelvin probe?
That's ex situ.
Ex situ.
Yeah, but the SEM, we have the optical imaging, that's in situ. This is in situ. So it's an optical cryostat, and you pass the current while you observe, and we also have SEM images in situ as well. So we put current while imaging with the SEM as well.
I see, and you don't see a difference then when you expose it to air afterwards?
No. I mean, there is probably difference, but it probably is the next term in a Taylor expansion.
I see. Thank you.
Okay, so now it's time to send the speaker. Perhaps
Oh, a diploma. Thank you very much. Yeah, thank you. Oh, this is very nice.
Now my pleasure to invite the next speaker. We will be talking about manufacturing of advanced nano-semiconductors and devices using a direct write technique. Maybe it's worth to begin with a pointer.
Okay, this is a laser. Okay.
So this is the same method was to initialize close to the electron.
Başlat sen oradan.
Let's see if it's working. Okay. Yeah. Okay. Thank you very much. Okay, so first of all, I would like to thank the organizers for giving me the opportunity to show my work here. And the goal of my project is the fabrication and characterization of advanced nanosuperconductors in the 3 dimensions using an additive manufacturing technique based on focused ion beam technology. The motivation of this project is the study of novel physical phenomena that emerge when a size of a superconductor is reduced to the nanoscale in the range of its superconducting coherence length and penetration depth. For example, superconducting vortices have the potential to be used as a quantized information carriers that could be used in the design of nanocircuits, and moreover, superconductivity can be modulated using an electric field as an external stimulus. So these nanosuperconductors and devices could serve as a building blocks for the applications in quantum computing and nanoelectronics respectively. So if we add in a curvilinear and 3-dimensional geometry in these nanosuperconductors, unconventional physical phenomena could emerge in which geometry, chirality, and topology could be interlinking. So these materials may hold promise for emerging or future development of multifunctional technologies. However, as you will see during my talk, there is a lot of work to be done in which, their fabrication and characterization remains a huge challenge. So this is a general sketch of the additive manufacturing technique. It is called focused ion beam induced deposition. The precursor molecule that I use for the fabrication of nanosuperconductors is tungsten hexacarbonyl. And those molecules are delivered from this nozzle and absorbed at the surface of a substrate, and the focused ion beam is scanned over the surface, partially decomposing those precursor molecules, forming a deposit. So in 2004, Saty and co-workers reported that these tungsten carbon nanowires run using gallium FIB presented superconducting properties below 5 Kelvin. It's a type 2 superconductor, S-wave, and the upper critical magnetic field was around 9.5 Tesla, and the superconducting coherent length around 6 nanometers. Later on, in my previous group in Zaragoza, we observed that this material follows properly the BC's theory, and moreover, we observed for the first time a direct thermally depending and melting transition of inner 2-dimensional vortices lattices. And what is happening when the size is reduced to the nanoscale, we observe a reentrance of the superconductivity as a function of the applied magnetic field in nanowires of 50 nanometers in lateral size due to a strong confinement of a single vortex row at the center of the nanowire. More recently, other authors have been reported tungsten carbon nanostructures grown using the helium beam, and later on using a different precursor material. And it's possible also to grow niobium carbon microstructures using the gallium focused ion beam. The superconducting properties of those materials are comparable to the superconducting properties of tungsten carbon wires reported previously. So let me just to summarize some of the results regarding planar tungsten carbon nanosuperconductor and devices. And first of all, I would like just to mention that in 2018, Jasot's group reported that superconducting methods could be modulated, the superconductivity could be modulated as a function of an electric field. And they experienced those effects in titanium, vanadium, and for example, aluminum materials. And these effects allows them the opportunity to create different kind of field effect transistors as this Josephson interferometer or gallium bridge field effect transistors. However, the mechanism behind this field effect is still very controversial. And in order to put some light in this physical mechanism and to see if this effect is extended to other superconductor materials, which are not purely metals, we created such a kind of field effect device using our tungsten carbon material grown using focused ion beam induced deposition, using gallium FIB and also using the helium beam. And we use the similar strategy that's used before by Yasotro's group. This is a typical SEM image of one of our devices. It consists of 45 nanometers wide and 3.5 microns long nanowire, and the gate voltages are these two, and the separation between the gate voltage and the nanowire was around 70 nanometers. And as Yasotro's group reported, we observed a modulation on the critical current as a function of the gate voltage at different temperatures. And we think that this effect is due to the squeezing of the supercurrent as a function of this electric field effect. And these experimental data are in good agreement with a simple theoretical model based on Gibbs-Landau equation developed by our chairman, Vladimir Fomin. So we wanted to extend these devices in a different material, that one grown using the helium beam. In this case, we used a wider wire, and even the separation between gate voltage is at least a bit higher compared with the previous device. And at the same way, we observe the same modulation in the critical current as a function of the magnet of the gate voltage at different temperatures. And just having a look at the transconductance, that is a figure of merit of the performance of field effect transistors, we obtain a similar values comparable with the transconductance values obtained in other superconducting materials, but even using a lower critical gate voltage. And even taking into account the critical current, the critical temperature of our devices, in principle, the applicability of these devices is in a wider range of temperatures compared to the other superconductors. So a summary of this first part of my talk, if we obtain a local suppression of superconductivity induced by an electric field, we obtain this superconductivity modulation at really low values of the gate voltage, and this gate voltage is comparable with those used in MOSFET technology, and we develop a simple theoretical model in agreement with the experimental data. And of course, this kind of devices could serve as a building blocks for cubic superconducting field effect transistor devices, Josephson junctions, logic gates, and single photon detectors. So let's move to the second part of my talk regarding three-dimensional nanostructures grown using focused ion beam induced deposition. In this case, I use a helium beam instead of the gallium beam, because the diameter of the helium beam allows you to create really nanostructures. That is not the case when we are using the gallium FIB. And I will just to emphasize, comparing with different techniques used for the fabrication of 3D nano objects, that focused ion beam induced deposition is very flexible in terms of shape and 3D geometry, as you can see here, and also regarding the resolution that you can achieve, that is in the range of the nanoscale. So you want to create real three-dimensional nanostructures with really high flexibility in shape and 3D geometry, the technique is focused ion beam induced deposition. So in this case, we can just find two examples of 3D superconducting nanostructures grown using gallium FIB. The first one was reported in 2010, some time ago, tungsten carbon wires, but as you can see in the SEM image, the resolution is pretty pure. I mean, the diameter of the wire is around 250 nanometers. Although the superconducting properties of these materials is comparable to the superconducting properties observed in planar structures. And in the case of niobium carbon nanowires, we had the same problem regarding the resolution, that is around 250 nanometers in lateral size. And also we observed that the superconducting transition is not so sharp as we would like to have it. And also in some devices, the resistance is not dropping to zero. So it seems clear that there's a lot of work to be done in order to improve the quality of the superconducting 3D superconducting nanostructures and in the for improving the superconducting properties. So I'm going to summarize some work already reported in different papers regarding 3D superconductors using the helium beam in order to get really nano superconductors and devices. And the first example is the fabrication of hollow nanocylinders, and it's a very simple way to do it, and it's the precursor molecules that absorb on the substrate, and the helium beam stays at the same position for the deposition time, producing two effects. The first effect is the growth of this nanocylinder. At the same time, the helium beam is producing a hole, a cavity at the center of the nanowire due to the helium beam milling. So it's just using that very simple way, you can create such a kind of hollow nanocylinders of 32 nanometers in outer diameter and around 6 nanometers in inner diameter, and the aspect ratio was around 200. So it's something that we cannot create by using a completely different nanolithography technique. So it's a really huge advantage. So what can we do? We can tune also the diameter of these hollow nanocylinders, just modifying the ion beam current. The ion beam current correlates with the ion beam spot, so we can just increase the size of the outer and inner diameters, just increasing the ion beam current. And in that way, we can control the 3D dimensions of these hollow nanowires. And here, interestingly, you can see in this 3D tomographic reconstruction how the cavity, the hole in these nanocylinders is starting from the top part and finishing at the bottom part. So with that, we can be demonstrating that we are able to create these hollow nanocylinders with at-will dimensions like hollow nanowires. So regarding the composition and microstructure of this material, we obtained that the grain size is around 20, 30 nanometers, and the crystallographic structure is compatible with the tungsten carbide FCC structure, and the atomic percentage of tungsten was around 72%. That if you have a look at this small box, those values are really good and better regarding the crystallinity and the higher tungsten content compared with tungsten carbon wires grown using the gallium FIB. So regarding the superconducting properties, we observed that those materials are superconducting as well, and the critical temperature is higher than those reported using the gallium FIB. And regarding the upper critical magnetic field, it's almost similar. The upper critical magnetic field is higher. So just using this very simple strategy, we are able to grow 3D hollow tungsten carbon nanocylinders using the helium beam with better resolution, higher aspect ratio, higher crystallinity, higher purity, and improved superconducting properties. So let's move into the second example of the 3D tungsten carbon nanohelices. We can see that just modifying two deposition parameters, that is not really complex, I'm able to tune the nanohelix diameter and the turn length of pitch between them. So just modifying these two parameters, I'm able to grow nanohelices with at-will three-dimensional geometry. And here I show you a few examples. I was trying to keep constant the diameter of the nanohelix around 100 nanometers, and the turn length is from 200 nanometers to 1 micron. And in the other way, 200 nanometers in diameter or 300 nanometers, and the turn length is from 400 nanometers to 2.3 microns. So it's possible to really tune the 3D geometry and the distance and the diameter between each turn and the nanohelix diameter as well. And the wire diameter is around 50 nanometers, the wire diameter of each nanohelix. Regarding the superconducting properties, I selected these 4 nanohelices in which I can compare with the same diameter, the smaller one, 100 nanometers at different turn lengths, and another diameter of nanohelix around 300 with different turn lengths. And I studied those superconducting properties using magnetotransport techniques. And I obtained very similar superconducting properties in all of these nanohelices in terms of the superconducting temperature, the critical temperature, the upper critical magnetic field, and even the critical current density that I was not showing here. So this is giving us an idea about the robustness of the superconducting properties of nanohelices with completely different 3D geometry. And interestingly, we observe a completely different behavior in one type of the nanohelix, in that one, and we observe here how the resistance as a function of the current is related at different jumps in the resistance, which are related to the occurrence of phase slips as supported by numerical simulations based on time dependence Gilbert-Landau equation, which is a collaboration with the Professor Fomin as well. And here we can see in the point number 4, for example, how the vortices patterns are inside of the nanowire, and in some moment when you are increasing the current, two large regions of phase slips were introduced into the patterns, producing that large jump in the value of the resistance. And in the second point, is happening almost a similar way. Two more regions of phase slips are inserted in the wire, and we observe again a second jump in the values of the resistance. So this is a demonstration of a proof that this three-dimensional geometry could tune the superconductive properties of these nanohelices, because of course this is not visible in planar stratas with the same dimensions. And well, the summary of this second part of my talk is that we were able to grow individual superconducting hollow nanocylinders and nanohelices with really small diameter and high aspect ratio. And this helical 3D geometry give us fingerprints of vortex and phase slip patterns experimentally identified and supported by numerical simulations based on time dependence Gilbert-Landau equation. And let me just to finish thank people involved in those works and the financial support of different agencies. And of course, thank you very much for your attention.
Thank you very much, Rosa, for a nice presentation. So,
on the first part of the talk, you showed this switching field, switching voltage, right, at 6 volts, which is much less than the previous ones reported. What's in terms of the field?
In the term of electric field,
yeah.
I have not these values in mind, but I'm pretty sure that this difference in the gate voltage is mainly because there are not metallic superconductors.
Oh.
And that's why the reduced value of the critical gate voltage that we need to apply to
so
modulate
this also leads me to the second question. So do you think there will be some peculiar materials? I mean, so they should be more metallic, these superconductors, with low resistance, for example, I don't know.
Yes, but in that case, for example, the metallic superconductors, at the end is you need to apply really huge electric field.
So the contrary, yes, the opposite, I mean,
exactly.
Yeah, okay.
And then is, for example, there's one example based on instead of carbon nitrides, superconductors, that they are not also too much metallic as well, and they obtain well, in the range of less than 10 volts of gate voltage to observe a modification or modulation of the critical current. But in that case, they induce higher values of the critical current instead of decreasing the critical current.
Okay.
But they were applying a back gate voltage that is not exactly the same that in this case. Then it's difficult to compare those different devices.
Okay, so you're feeling it's more resistive, it's better. Okay, thank you.
Yes, well, semiconducting, you know, yeah.
Concerning that first part, I mean, the controversy with the results from Chiassotto is actually the leakage current.
I know it.
So did you mention that?
Yes, exactly. Yes, I was introducing the gate voltage using a Kissley, and the same moment that you can just tune exactly what is happening. I mean, you introducing voltage and measuring the current, and the values of the current that they measure were negligible compared to the critical current that the current that I'm introducing in the bias system.
Okay.
So one of the ideas is just to try to increase the separation between the gate voltage and even decrease the lateral size of the gate electrodes just to confirm and to see that there are not any kind of relation between this leakage, or at least, I mean, normally there is a leakage in any field effect transistor. No.
Because I mean, we tried to do something similar, but it's always leakage.
Okay. Mm-hmm.
Yeah, can I comment on that? So I appreciate you say it's a controversy, but indeed I also really agree with you with your suggestion. And for me, it sounds like strange. It's not has been done. Is to do scaling with the size, because we together with Alejandro with similar experiments and saying there is no leakage current. For me, it's like how many current you need. A single electron with an electron volt will be enough, and your Keatley will not detect that. So I think.
Yeah.
I fully agree with you. We should do the scaling and see that the voltage scales, and that would be right. Finally, stop the controversy. I think.
Yeah, no, I fully agree, because it's something that it's clear that there are some parts that it's just energetic electrons that are trigger the large amount of quasi-particles that drive back the superconductor to the normal state, and it's clear that it's very important to know exactly what is the mechanism behind of this field effect, to know how to solve this kind of problem, because leakage in a field effect transistor is also one of the problems for the performance of such a kind of devices.
Yeah, but then I think your technique is really powerful to solve this question. So that's what I want to say. It's a positive thing. I would say this is perfect for tackling that question once and for all, and to get rid of this controversy, I would say. Thank you.
You're welcome.
So it's now time to thank all the speakers for the first part of the session. It's my pleasure to send you the certificate to you, Raja.
Thank you very much.
Contribution to the conference.
5 minutes break.
Okay.
So, thank you very much for the introduction and to the organizers for inviting me to this beautiful place. And being on the road of thanking, I would to thank my collaborators in this work. So, most of the graphs I will present are from Bernd Eichner's PhD thesis, additional material from the thesis of Lukas Backmeister and Philip Korner. We had some help from Barbara Budinska, who is a PhD student from Alexander, and the samples were prepared by Max Kara, Katja Wulster from Dieter Kölles group in Tübingen. Well, it's working. I'm lucky. So, thank you for the techniques. This diagram is well known to everybody in the audience. I need not mention more, except maybe that the vortex state in the copper oxide superconductors is much more extended that you see in this textbook graph. So Meissner state is very little, and there is a huge upper critical field. So whatever you do, practically you are mostly in this vortex state where the vortexes penetrates into the superconductor, and for technical applications you usually do not like this. So many concepts of pinnings have been explored for technical applications like tapes and so on, usually by introducing arbitrarily distributed defects, either during the fabrication by nano-inclusions or by irradiation with swift heavy ions, for instance. So producing pinning is quite a common topic from the very beginning of the research in copper oxide superconductors. But there is another thing which could be interesting, which is explore pinning of regular patterns, so that you can design any pattern you would like to have. And this cannot be done by these previous methods because they have some arbitrary distribution of pinning centers. And for all of these pinning explorations, there is one condition which is important. The distance of the pinning sites should be smaller than the London penetration depths. And you can hardly reach this in classical superconductors like in niobium. You need to go down to like 40 nanometers. And in typical high-TC superconductors like YBCO, you would need like 150 nanometers, which is kind of far below what you can do with conventional lithography. So there are several types of defects you can introduce, and I would like to introduce you to the Vienna Zoo, which is the oldest one in the world. So sorry for this product placement here, but we can use several kind of animals for explaining the different pinning sites. So the hexagonal lattice, as you see it in a turtle, is the state which you have in a clean superconductor. It's quite well known. It might even have some little distortion, but this is quite common. If you introduce point defects, you have something like the cheetah. Random point defects can be either intrinsically by atomic displacements or lack of some atoms, interstitials, and so on, or you can introduce them by soft irradiation, like electron irradiation, proton irradiation, light ion irradiation, and so on. And this gives typical way of pinning the vortices in an entangled form, which we'll discuss later on. Another thing is the tiger, which has kind of nano, or kind of one-dimensional segments of pinning sites. This typically can be introduced by self-assembling of defects like this barium zirconium nanorods, where you have pinning sites which are one-dimensional but do not extend over the entire sample. And the next step in progress would be the antelope, where you have these pinning sites over the entire depth of the sample, but still arbitrarily distributed. This is what you have when you irradiate with swift heavy ions, for instance, and these are the defect tracks you create with the ions. But what we want to achieve is something like in the emperor's anglefish, a pattern which goes through the entire sample and is equally spaced, so is regular. But unfortunately, in all these attempts, we might end up in something like a tapir, which means we have some of these extended one-dimensional defects, but in addition, we have some point defects in between. So this will be kind of layout of my talk. Well, Alejandro has already mentioned the delicate structure of YBCO. So I come from another point, so I do not use high electric fields and currents, but basically the thing is the same. This copper oxide chain oxygen atoms are very weakly bound by 1 or 2 electron volts, can be easily kicked around, also by irradiation. And this can be done, for instance, by a focused helium ion beam, so a little bit similar than Rosa told us. We use a helium ion beam, which we can scan over the surface and blank it, and by that we can, in principle, program any arbitrary pattern which we like to see. This is more or less equivalent to a superconductor with holes, not exactly, but more or less. And if we apply a magnetic field perpendicular to the surface, we can find a particular field called the matching field, where a flux quantum penetrates every hole, or in our defect nanopillar in our case. And there is a easily to calculate field where this matching or commensurability should occur, which is just given by the area of this defect lattice and the flux quantum. Now the instrument we use is a helium ion microscope, which we use in a kind of modified fashion. It's built for making pictures. We force it to destroy samples, which is a little bit different. So rather intense ion beam is focused on the sample surface. And contrary to the original design, which is a very sharp beam, like half a nanometer diameter, we widen it up a little bit because this is more favorable to get a more homogeneous kind of nanopillar in our system. What we can achieve, for instance, this is a picture of 20 nanometer spaced hexagonal lattice of such nanopillars viewed from the top. And actually our samples, where we'll present the measurements later on, do not look like that. So we have exaggerated the fluence very much to visualize. So these are essentially blisters. So we really destroy the sample here. In original samples which we use for measurements, you don't see anything, because we just kick around oxygen atoms, mainly oxygen atoms, and do not destroy the crystallographic framework of the entire structure, so it's not visible. And from a side view, it looks like that. If the dose of ions is rather low, you don't see anything. If it's a little bit higher, you see emerging of one of these nanopillars. If it's even still higher, you see an amorphized zone of about 7 nanometer, which means the stronger you hit the sample, the wider is this pillar. But this is with focused, strictly focused ion beam, and when we widen it up a little bit, we come to this situation here, where we don't see anything, but still have the effect on the transport properties. But we should understand a little bit what's going on in transport, and for that, we irradiated samples flatly, which means without any particular structures, just by overlapping the beam, very widened up beam and overlapping, so it's a homogeneous fluence over the surface of the sample. And we see resistance, so TC goes down, obviously, resistance goes up, and there is one kind of common knowledge how to interpret such resistivity curves, and this is that the slope more or less corresponds to the inverse carrier concentration, and the offset corresponds to the number of defects you have in the sample. So essentially, the oxygen content is not changed at reasonably low fluencies, but defects go up, and the same finding you can also see in the Hall effect. Nevin has elaborated on the strange Hall effect in YBCO, but we just use it as a simple probe. So here we use the inverse Hall angle, which is a probe, according to Phil Anderson, for both number of carriers and defects. So it's quite a similar formula if you scale it like that. And you see the same. You see essentially the same slope and an increase of the defects. So what we know is we induce a lot of defects with the irradiation, but we do not lose oxygen. We still have fully oxidized YBCO. With this data, we can carry on and try to simulate the three-dimensional structure of these nanopillars. There is well-known software for that, the SRIM trim package, but this gives only the defects per atoms, which you see in this example here. And the defects per atom can be kind of parameterized by experimental data to TC. And this is just by using what we had before, so taking the resistivity data, taking the onset of TC, plotting this along the dPA, which we have from simulations, actually from plane field simulations. And then we see this nicely follows the Abrikosov-Gorkov pair breaking theory, which on one hand might be a little bit of a surprise because the theory is for magnetic inclusions, but it's well known that since YBCO is a D-wave superconductor, also elastic scattering on point defects are pair breaking, so it goes with the same Abrikosov-Gorkov law here. And this curve we can now use to calibrate. We can go from a dPA value to the curve and then to a TC, and using that we get the structure of our nanopillars. So you see, essentially the red one means TC is fully suppressed, and the diameter is something a little below 10 nanometers, what we can achieve. This depends a little bit on the fluence that we use, but essentially the trade-off is if we use too high fluence, we have amorphization and wider nanopillars. If we have too low fluence, TC is not fully suppressed. So it needs some kind of delicate adjustment of the parameters to get where we want. Okay, but nevertheless, we have an idea what's going on from these simulations, and we use them to see what is the limit of this method. So how dense can we make these patterns? And you see some of the simulations here, a 30 nanometer hexagonal lattice, 25, 20, and 15. This is very well developed, as you see. This is a top view, this is a side view where you see these channels. And with the 50 nanometer, obviously, there is no percolation path anymore, which remains superconducting. It's exactly what we see in transport measurements. So we have the different lattices. Some of them have only slightly suppressed TC, and the 50 nanometer sample is semiconducting. So obviously there it breaks down. So we will focus on the 20 nanometer sample. The fact that TC is a little reduced is just by the fact that we have some minor defects from straggling of the ion path. So these trajectories are not exactly parallel to the z-axis because there are collisions and there's always straggling a little bit, and we have some minor amount of defects in between, which by the same law as I have shown before also reduce TC, but fortunately only a little. So with this 20 nanometer spaced lattice, we can measure critical current, and what you see is a peak in critical current at 6 Tesla, which to my knowledge is quite a record high field, because previous works were more or less limited to the range of 10 or 100 of millitesla. And so this is a clear peak in the critical current. It becomes even more obvious if we normalize to this peak. Then you see that at a little bit elevated temperatures, so the color coding is here, maybe at 25 Kelvin, we have a very pronounced peak already. It's just not seen very well here due to the scaling. So obviously, if intrinsic pinning is not that strong at little bit elevated temperature, then this artificial pinning, which we introduced, becomes even more prominent. So one important point is we have this commensurability at very high magnetic fields. These are fields which are typically in previous explorations of arbitrarily distributed defects, like heavy ion irradiation. So these people were in the range of several Tesla of matching field, but they did not see any peaks because it was an arbitrary distribution of the pinning sites. The second part, which is also quite interesting, is that now we can have commensurability effect over the entire transition. So you see here is 2 Kelvin where we see already something, and this goes up to, let's say 55 Kelvin. If I remind you, the TC onset of this sample was 50 Kelvin. So we see it up almost into the normal state, which means that at the first bending into the superconducting transition, we have not a real vortex liquid, because then it would have no commensurability effect. We have kind of a plastic flow of a vortex ensemble. So this goes up to really high temperatures. Yeah. Then we go back to the 30 nanometer sample, because this had this very nice contrast. It's obviously a little better than the 20 nanometer sample, has a matching field of 2.6 Tesla, and explore the critical current. So critical current there is very remarkably, so this is scaled to the one at p equals 0. And you see it's going up to quite high values. If we take, let's say, 40 Kelvin data, this is the pink curve here, then you see it goes up to 80% at 2.6 Tesla, which is quite remarkable because we can compare to films. So I took one recent work which is quite representative for several published works, but they had data exactly also at 40 Kelvin, so I can directly compare. This is the main advantage. And you see at the same field, and where is our matching field, a genuine, so a non-processed YBCO sample has dropped down to 25% of critical current. And even with this BCO nanorods, which is the tiger structure, it comes up to 40%. And if we take just this data and plot it here, you see it looks like that. So at high fields, it rather well matches our curve in our sample, which is the pink one. But in this field, you see this very pronounced peak. At very low fields, our structured sample even fall off a little bit more rapidly. So we would say this is close to this anglefish structure what we have produced here. But we would explore the critical current a little bit further, because critical current is a very diffuse thing. You know, this is a voltage criterion. If you have very good equipment, then you have very bad samples, because you can measure to very low voltages, which reduces the critical current. So critical current rather has to be at least checked or explored also by IV curves. And if we do that in that sample, and actually at the point where we have this maximum critical current, so at the 2.6 Tesla, we see something like that. There was this old question, is a dirty copper oxide superconducting a real superconductor? And it's many years ago when it was raised, and it's longer time ago already solved. But the point was this: if you make these IV curves, take this red one here, then you see there is a ohmic region. It looks a little bit distorted, because it's just a projection. So it's strictly linear here in reality. And this is attributed to the well-known thermally assisted flux flow, which means that the temperature is high enough to activate your flux lines. And even at the lowest measuring currents, you have a finite resistance, which means that these lines here, even if you go to extremely good instrumentation, you still can detect resistance, because resistance basically is the same all over here. And this tough regime happens at somewhat higher temperatures. But if you look carefully at such data, and they are not different from data, or they are qualitatively not different from what you have on a plain YBCO film, for instance, without any patterning, so there is a positive curvature. Then it goes over to a negative curvature, and there is some separation line, which is green here, where it's a power law behavior, what you can see here. And the theoretical background also is quite old and very known since a long time, which are the vortex glass theories. There are essentially two which are relevant for my talk here. The vortex glass, initially proposed by Fischer, is for zero-dimensional defects, or point defects, the cheetah situation. And the Bose glass is for one-dimensional defects. Essentially, this is the situation of the antelope. And both theories predict a very particular scaling, which is this seemingly complicated formula here. But as you see in a second, if you apply this formula just for scaling the axis appropriately, you end up with something like that. So these f are universal functions which are unfortunately look a little bit different here in the view graph, but this should be F plus and F minus. And all this data you see here can be collapsed to two universal curves. And this function F is in principle not known, but is characteristics for a particular class system. So this is a very genuine and very fundamental theory which does not put anything inside like particular structure or material or something like that. If it's a second order transition, which is a glassy behavior, it should end up that according to this formula, you should be able to scale all this data in the vicinity of the glass temperature. Obviously, there is a validity range as in any second order transition. It does not be valid indefinitely, but you see it's quite a large temperature range which could be collapsed here. And this theory has essentially three parameters. One is this glass temperature, which separates these two branches. And there are a static exponent nu, which essentially tells you the correlation length of the glass or the fluctuations of this glass. And a dynamic parameter, the set, which tells you how it reacts to dynamic excitations, in particular also to alternating current and so on. So we did this many years ago, where you can explore the phase, and then you see the glass transition also in the phase. But this we don't do here. We just keep with these three parameters. And you see, as a comparison, I have now plotted the top two curves are at matching field, and the other two are off the matching field. And you see there is a very distinct change in the properties of the system, and particularly this dotted line, the separatrix, which virtually presents the behavior exactly at the glass temperature, is quite different. So you have here I to the fourth and I with an exponent 2.75. So which means if we are in this matching condition, we have a definitely different vortex dynamics than offside this matching condition. Putting these parameters in graphs, here is the behavior of this glass temperature independence of temperature and magnetic field, kind of a phase diagram, which we know from several other things. And this dotted line here is how it looks like in a plane ÜPCO film. So it's an essentially linear decrease of the glass temperature with the magnetic field. But if we pattern our sample with this particular structure, you see there is a strong bump in this phase transition boundary at the first matching field, and also a minor one at the second matching field. Second matching fields means that we have two vortices per unit cell of the defect lattice, but we do not exactly where the second vortex sits. There is the possibility it also sits in the defect, but it's repelled, so we have kind of elastic force on the vortices, or it might sit on an interstitial position. So we cannot ultimately clarify this at the very moment, but obviously it's another form of commensurability as well. Good. Taking these parameters, now this nu, as I mentioned before, the correlation length is very insensitive. Both in theories and also in experiments, we see there is no particular feature as our matching fields, but the dynamic parameter, which characterize essentially the movement of vortices, has a very pronounced peak exactly at the matching, which we would attribute to the fish scenario. I should mention the theory predicts both for vortex and Bose classes. Interestingly, also the theories are from the concept are substantially different. They come to very similar critical exponents. So from these data, it's not possible to discriminate between a vortex or a Bose class. So means zero-dimensional or one-dimensional pinning. This would be this gray area, so between cheetah and antelope, basically this can be discriminated by angle resolved measurements, which we did with some other samples before, so we are pretty sure it's a Bose class, and this is very natural. But going back, this peak goes very much outside of this validity range from the theory. And the theory is made for arbitrary defects, not for regularly spaced defects. On the other hand, we know if we have a first order transition and a sharp melting of actually a lattice would be then a vortex Mott insulator, and I think we will hear more about vortex Mott insulators later, then this set should essentially go to infinity, which means a higher set is an indication of a higher degree of ordering. So this is here, and if we tune the magnetic field of the matching condition, we, oops, oh, I did a mistake or not. Oh, but I did not press this dangerous button. Okay, oops. Back. Almost have it. Yeah, here. That we have this Tapir situation. So we have a mixture of pinned vortices in the defects, and we have some pinning in between. And in these intrinsic defects, we still survive in between. And we want to call this an ordered Bose class, kind of a new observation of a phase in such vortex system. Why ordered Bose class? Because it scales like a Bose class, which means it's not a crystalline lattice of vortices, or it might be a vortex Mott insulator excited to higher temperatures, but also with additional defects in between. But in contrast to a regular Bose class, it has this pronounced peak and this higher, let's say, steepness of the transition at the matching condition. So I think my time is almost over. So just to mention that you can use this technique as well to produce other lattices, like a quasi-Kagome lattice, where you can explore competition between elastic energy of the vortex lattice which wants to restore the hexagonal lattice and a distorted one. And these are some older results, so I have presented them before. And essentially, I come to my conclusions that with the helium-ion microscope, you can produce nanopillars in YBCO films on a very dense scale, which you can use for playing around with different vortex matching effects. So one we have demonstrated is matching at 6 Tesla, and the other thing which we found and which we propose to call it an ordered Bose class when we have pinned vortices in an hexagonal lattice plus intrinsic defects in between. Thank you very much for your attention.
The presentation is open for questions.
So I have a question concerning the first part. YVCO with you grow it on top of STO or?
No, it's LSAT, lantern strontium aluminum.
And do you know if the helium goes through? Reach the substrate?
It definitely goes through, at least from simulations.
Yeah.
And this is the idea, because we want to have the defects penetrating our entire YBCO field.
But how much it modifies the substrate? Because I guess that
much less than the YBCO, because the substrate is more rigid in some sense. It does not have this movable archisense. But if we amorphize the YBCO, then we see some growing of the crystal lattice of the substrate as well. It's not what we do for the experiments, but Dieter had made some, or actually not Dieter, but we have some data on transverse high resolution TEM, where it's irradiated by far too high fluence, and then we see the YBCO is blowing up, and also the substrate is deformed a little bit.
I wonder if it's not possible to irradiate first the substrate and then grow the YBCO, because I will change the property of YBCO as well in a more columnar way, and that can go much higher, much more than the range of the penetration of the...
Yeah, sure, you're right. So this would be kind of a templating strategy.
Yeah, right.
Might be done.
Any further questions, please?
It might be a silly question, but have you considered strain effects on the crystal, or is it completely irrelevant?
For transport is rather irrelevant, but we are sure that strange effects are there. So there is no doubt. We know from plane irradiation where we have X-ray data that, for instance, the Z-axis distance expands a little bit due to reshuffling the oxygen from their chain positions to some interstitial positions, and this expands a little bit. But I guess it would relax in a few elementary cells but it doesn't pose any problem for us. If it is too strong, it would just reduce our transport, so the TC in between these nanopillars.
Okay, I think we have no more time. Would you like, please?
And very quick one.
Very
Do you,
very short.
since Dieter ran on that big express of green managers and junctions, have you ever thought of if to please these defects would improve the quality of your junction by creating your junction?
Actually, something Dieter and me have already on the radar.
Okay.
Yeah, because we can evacuate flux and all these concepts.
You've been
Good. Now I have the pleasure to invite my co-chair, David Massarotti, to introduce you as a different.
Thank you very much.
Hebrew University of Jerusalem, and he will talk about the vortex dynamics in ferromagnetic superconducting bilayer.
Okay. This not. But so down is up. Okay. It's tricky. All right. Good morning, everyone. So as the chairman says, I'm Yonatan Anauri from the Quantum Imaging Lab at the Hebrew University. So let me first thank the organizer and the chairman for inviting me and giving me this opportunity. I'm very, very excited to present you this result today. It's the first published result of my lab, and we're very excited about it. And this sort of artist perspective summarizes at least the first part of my talk. So it's edge magnetism, and it's also its effect of the magnetic structure on the vortex dynamics. And this thing here is the technique that we use, which is the squid on tip, that I will introduce briefly for those of you who don't know. So the scanning squid on tip microscopy is a microscopy technique that allows magnetic and thermal imaging at the nanoscales. This is an SEM picture of one of our device, a relatively big one, which an outer diameter of about 160 nanometer, and the way it's built on a quartz pipette, and or a glass pipette, and there are two lead leads here that are superconducting that are separated here by a non-percolating gap. And the idea is that these two lead leads meet at the end of the pipette where the squid lobe is formed. And that allows us to have a squid that we can bring in very close proximity to the sample. And we can make them relatively smaller, below even 40 nanometers. And the idea is to strap this to a scanning probe microscope and to do magnetic and thermal imaging at a nanoscale. So just quickly, the features, so it has a suitable geometry. Why? Because it has a very small loop, and we can get this loop very close to the sample. As a result, it is extremely sensitive. We're talking about sensitivity to a magnetic moment that is smaller than 1/3 of the spin of an electron. Or if you're talking about thermal sensitivity, which I will not talk in this talk, but the sensitivity is better than 1/1,000,000th of a degree at 4.2 Kelvin. And all this with a high spatial resolution, and we can work to a relatively high field, which is not the case for other scanning squid techniques. So I've been in this business for more than 10 years now as a postdoc and as a PI. And sometimes during the coffee break, people would come to me and say, wow, is it that simple? Like, you make it sound a little trivial. And back then, I would, as a postdoc, I was like, well, nothing is trivial, but, you do what you got to do. And, at some point it works. Little did I know that to create this operation on your own, you need to solve what I call the multi-scale problem, where on one side you have meters and tons of rock that you need to plan, and the displacement and so on. And on the other hand, you need like a nanogram and a nanometer that you need to plan. And all this at some point, after the planning, manufacturing. This is me. If you were wondering where I was during the couple last year, I was there in the bottom, the lowest part of the lab. And you throw some students in the mix that are naive enough to think it's going to be fun to join this new PI and have a good time, and they're brave enough in a certain sense. And then you get a working microscope. And so the lab is now running for a bit more than 2 years. And we've been exploring several topics, going from superconductivity, magnetism, this is the material I'll be talking about today, but also magnetic vial semi-metal. And we have a new work now that we just submitted on vortex diodes in ferromagnetic superconductor heterostructure. I took the liberty to add vortex braiding, which is something that is we're really excited about. So I will add this even though it's not in the abstract. So the material I'll be talking about today, the magnetic material, is a chromium germanium telluride, or CGT. It's what you need to know is that it's essentially semiconducting, so it's not conducting at low temperatures. It has a ferromagnetic transition at about 60 K. So people, looked at these, and it's exfoliable, so people look at these flakes. And one of the way that you can look at these is by proximatizing with a metal and looking at anomalous Hall effect. And what people have seen, other groups, was that you get a small but finite anomalous Hall effect at zero field. So, and they've also managed to do MFM at the same time. So when the sample is fully magnetized, here you see that almost no features on the image. When at some point you get this step in the anomalous Hall signal, this coincides with the appearance of some domains. And then you lower the field, you reverse the field, these domains seems to evolve, and then you again saturate the magnetization on the other side. And this is also true for the lower branch. But the fact that they see here a finite signal lead them to think, okay, this material retains a finite magnetization at zero field. And we believe that this is not the case for at least most of the sample, but we'll talk about this in a moment. Another experiment, and this is more related to the title of a vortex dynamic, another experiment that you can do is to proximatize this ferromagnet with a superconductor and measure just the longitudinal resistance. And this was done again by another group, and where they found that actually at a constant current, if you look at the magnetoresistance, you have an hysteretic behavior that seems to be somewhere around, some sort of coercive field or so on, and they were not so sure why, how to interpret this data. So this was a good opportunity for us, wherever there is a unsolved transport mystery, maybe a microscopy can help. So the first thing is we did the same heterostructure in our lab, and we managed to get a similar behavior. And but we have the advantage that we can have a look at the same time with our microscope. So what I'm going to show you now is a movie of the magnetic structure evolving. And here you have the transport. So now we're at the zero voltage state. And I'm going to raise the field, and you're going to see what happens. So I'm raising the field here. You see this magnetic structure is evolving. And at some point it becomes very flat. And this is where the resistance starts to go up. On the way down, the magnetic domain appears and coincides more or less with the zero resistance state. And we interpret this as a vortex physicist as a pinning potential. So if you have a very disordered magnet that has a very non-uniform pinning potential, that it pins vortex very efficiently, whereas if you are fully magnetized, then the pinning potential becomes very flat and flux flow can happen very easily. So this is So we kind of, find an interpretation for this phenomenon. But what we found out is we can maybe use this as a way to probe the magnetic state. So why am I saying this? Is because when I look at one image, so this image was prepared. This image is taken at 0 applied field, but it saw -1 Tesla. And this image here saw +1 Tesla, but again take it at 0 field. So which one is magnetized, which one is not? Is there a net magnetization? It's very hard to say from the image. So you need some extra another probe that is more global to tell you what is the state. And here what I will do is I will again show you the transport data for these two samples going up. So if this sample has more domains pointing up because it was at +1 Tesla, it should magnetize more easily in that direction because there will be more domains pointing in that direction with respect to this one. And we can look at both images and at the transport data. And now I will run the movie again. And as you can see, both in the images and in the transport data, these two things coincide each other, which mean essentially that the sample has no memory. It's at 0 field. Magnetically, it doesn't know if it was at -1 Tesla or at +1 Tesla before, way above the saturation field in both cases. It starts from 0. It doesn't know. So it's not magnetized. We don't need to go all the way to 0 field. So this is when we go to 0 field and go up again. We can stop, go down, and stop and start to go up here. It's the same thing. Right here is the same thing. And you really need to stop in the middle of this voltage state to go up on the other branch. So basically, as soon as we start seeing those domains, the sample, the magnetic sample forgot where it came from. So I bring you back to the initial data that I've shown, and where I told you these guys measured a finite anomalous Hall. Why is that the case? And we thought about many different interpretations. Maybe it's also the effect of the platinum that hybridizes and stabilizes the magnetization. But maybe there is like a tiny part of the sample that does stay magnetized, and we're missing it, even with this transport measurement and even with our imaging. And after looking for a while, we saw that actually the edges of the sample remain magnetized. So this is at the sample. This is the sample interior. This is the sample substrate. This is the edge after an excursion at +1 Tesla at 0 field. And this is the same area of the sample at -1 Tesla. And you see that the edge stayed magnetized but revert the orientation. So, and we tried this this is at a slightly thicker film, and we also see this effect. So now, why would the edge be magnetized? The truth is we don't really know, but we have a hint maybe. So we looked also at the behavior of the interior as a function of thickness. So this is for very thick. We said there is no magnetization here. When you increase the field at some point, it magnetizes. And so I can draw this with my hand, like just a magnetization that goes up until it saturates. And if I go back to 0, it goes, it stays magnetized, and at some point it demagnetizes and it stays here. So I can just anti-symmetrize this picture. So this, we call this the bow tie magnetization curve. And however, so if we are below a certain thickness, around 10 nanometer or so, the sample stays magnetized at 0 field. It does go through a coercive field, as you would expect from a standard magnet. It does saturate. And if you go back to 0, so it does something like this. It reverses its magnetization. And if you go back to 0, it stays magnetized. So for thin films, it behaves like a hard magnet, and for a thicker film, it behaves like this bow tie. Okay, so I complete the picture here. Okay, but what does that have to do with the edge magnetism you're saying? So if you look at one of these edges, if you look at, I take here a cross section, I get this peak, and I look at it in the TEM. Well, in the TEM, you see that the edge of these exfoliated films, they're always sort of in a wedge shape. So they have actually a distribution of thicknesses, and there's always a part of the sample that will be thinner. So we think that, and if we indeed consider this part as being a magnet, and we know how many Bohr magneton to expect per chromium, we can actually simulate this peak rather well. So you can say, okay, but how do you know that is the distribution of thickness? There's a lot of things that happen at the edge. There is like dangling bonds and the unsatisfied bonds, and that could also be the case. And that's, if you think that, you might be a referee number 2. But, we thought about it for quite a while until we realized that there are other edges. So this is an edge, but there's also step edges between two terraces. And at this step edge, you have the same dangling bonds as in an edge, but if you're above the critical thickness, you should not see anything. And it turns out that we had this data, AFM data of these terraces that happen naturally in these van der Waals materials, and you see these nice steps. And this is the image of that area at zero field. We see absolutely no edge magnetism in the case of step edges. So it really seems that it needs to be at the edge of the sample to be magnetized. So partial summary, thick films, no magnetism in the interior, only at the edges, and thin films below 10 nanometers, so behave like a hard ferromagnet, or if you want the artist's impression to remember it better, take it home. So now let me switch gear to the bonus material. So if I say braiding, most of you have something like this in mind. I see Roland is in the audience. So he showed us some nice way to do it yesterday. And people usually think of wires with piano gates, and then you can tune part of it to be in the trivial state and in the topological state, and you have Majorana at the edges. But there might be another way to do this, and it's with vortices. And this is the avenue that we want to present now. So we call this an on-chip braiding device. So braiding vortices using scanning probes was done before, but the problem with this is that it requires to have the scanning probe. We're trying to do it just on-chip. So the way we do it is that we take 3 superconducting loops, we separate it with an insulator, and we put another superconductor on top. So this brown layer we call the control layer, and the green superconducting layer we call the target layer. And this is how it looks like looking from the top and the SEM. And the idea is that you can put vortices in this layer, and maybe you can manipulate them. So if you and the idea here is that we use our microscopy technique not to move vortices, but only to image, to validate our design. So if you cool down at a certain field, you see here a bunch of vortices, and you see here exclusion zones, okay, where there are no vortices, and that makes sense because there the vortex need to thread through 2 superconductors. But what you see here is that there are 3 vortices at the 3 central point of these loops. And if I cool down with a lower field, I can get just a few vortices. And what I can do is that I can apply a current in one of these loops and kick this vortex out. Now, if I reverse the current, I can bring it back again. And I can put it here, and then maybe I can absorb it with the other guy here. And essentially, I can sum all these steps and play with these vortices. And that's what I'm going to show you now. So we can actually pull the vortices and exchange them, wind them, and braid them. Of course, here it's a niobium diselenide. The target layer is niobium diselenide. I'm not claiming there's a Majorana here that is being braided. But let's say that would be a step let's say one element of the toolbox if one would want to do it using vortices. And again, I leave you with a partial summary of the artist impressions. So there are 3 loops with this vortex in the middle that you can play around with. And with that, I would like to thank the students and my collaborators. So Avia Noah, which is here, who did the CGT work with the niobium diselenide, and Itai Keren, who did also the work with niobium diselenide on the vortex braiding. And I would like to thank you for your attention.
Thanks for your presentation, and we have time for questions.
Yeah, thank you for the nice talk. Just technical question. How do you control the vertical position of the tip while you're scanning?
You mean the...
To set the constant...
okay, so we couple it to a tuning fork.
Okay.
So we don't... so the coupling is not ideal, and we only poke. Like, we don't control it in real time. So we don't have a feedback mechanism. We touch, retract to a certain height, and scan.
Okay, yeah, thanks.
So how fast can you scan a square micrometer? Like what is the...
So like this image is a 6x6 micron. It took about 2 minutes, but so a square micro, I mean, it depends, resolution, signal to noise, and so on. But it's of the order of minutes, I would say.
And for the magnetic material, I mean, as far as I understand, you consider the number of layers at the edges, but you know, oddness and evenness of the number of layers may also have an effect. Have you considered that, or?
We haven't seen any odd even effect in the interior. It seems that all the thicknesses that we looked at behave the same, but we haven't counted. But you know, unless we always had the even number by magic, then I guess we probe both of them. We haven't seen any effect. It's also a ferromagnet, not an anti-ferromagnet. So in that sense.
Thank you.
We have time for one more question. If not, let's thank the speaker.
Bit up? Higher? Okay, sorry.
So next speaker is
Let's
Joris
try,
van der Wolden from University of Leuven, and we'll talk about molybdenum germanium
Not yet working.
as a building block for new superconducting device concepts.
Okay, everything works, perfect. So thanks for still being here before the lunch break. So let me first introduce myself. As already said by the chair, my name is Joris van der Vondel. I'm working at the Catholic University of Leuven. And today I will present our work related to molybdenum, germanium nanobridges as building blocks for new superconducting device concepts. So this is based on this work, which is referred here at the bottom. But okay, keeping track of time. So actually, I should also thank the organizers. I think that's also important for having me, giving the opportunity to have a talk. So thanks for that, and organizing this very beautiful conference. Let's start with the more important things. And then I think I also have to thank a lot of contributors. So we have the team in Leuven. Actually, the main protagonist here was Lucas Nulles, a PhD student, and Helene Darcy. But there is also a very strong collaboration on IMEC, which is actually a research institute next to our university, which are really pushing forward quantum technology. Then we had a visit of Davi, who actually also participated in the memory devices. And a very long ongoing collaboration with the group of Professor Siranek, because I think these nanowires can be tuned very efficiently using electromigration. And finally, the simulations I will show here today, the time-dependent Ginsburg-Landau simulations, are done in the group of Antwerp by Professor Milosevic group. Okay, so I think compared to the previous talks, it's very simple, the basic building blocks of my talk, and they are summarized here. So we have a simple constriction between superconducting banks, which is a nanobridge. I think the simplicity is also a bit of the power and beauty, because you have, let's say, if you see to the current phase relationship, you have, to some extent, at low angles, a linear current phase relationship, which bends off at higher currents. But the nice thing is that it's tunable, and it's tunable in the sense by very simple and conventional nanofabrication through tuning the width or the length of this nanobridge. So you have a very nice control in nanofabrication, from nanofabrication perspectives. Then a final ingredient actually is we put them in a loop structure. So we have flux quantization, and this gives us actually possibility to tune the vorticity winding of the phase in these devices, which actually gives also access to really read out the exact current phase relationship of these devices. So that's the two basic ingredients. So let me summarize, and I think why nanobridges. The first and simple ideas one can make, as also discussed in the talk of Jonathan Anahori before, is it's a very easy way to make junctions. Of course, it's on a tip, so it's much more complex, but the basic idea is you can simply fabricate nanobridges, and as well you can tune these nanobridges. For example, through electromigration, we put here an aluminium squid, we can send current through the squid, electromigrate, and we can actually change the current phase relationship. Or as also discussed today, you could also gate it with an electric field, so it gives a lot of potential and flexibility and combined with simplicity. What we want to move for, but I will not show today, but I think we have first preliminary results, is to, one can also make a flux qubit, predicted by Moy, and actually developed, or experimentally verified by the group of Astafiev, You can make a flux qubit by just simply embedding a nanowire into a superconducting loop. So, and again, there is this nice flexibility. You don't need an oxide layer, so it should have potential applications, potential applications in qubit technology. And finally, I think there is also some recent development. One example is here. Since we now have, let's say, these low temperatures, we can also think not just only for qubits, but for other simpler memory type of devices. One can use these loops as well, and I hope to show you at the end of my talk. Okay, so the outlook or the ambition today is I want to show we can control the kinetic inductance, so it's by simple nanofabrication. Then we can understand the absorbed vorticity state. So this is a very standard experiment. Many people do that. You just do IV sweeps and you measure the critical current. And then you see, actually, depending on the vorticity, you see different critical currents, which are used, for example, as sensing purposes. But we wanted to really basically understand how the observation comes to life. And I think we finally, or let's say we get this. And then a final slides of my talk is about once we understood all these concepts at play, try to develop novel devices. Good. So as shown here, so this is the fabricated, so this is the workhorse, so this is the device. It's very simple. There is one e-beam run. We do molybdenum germanium with a PLD system. It's a 25 nanometer molybdenum germanium, and then we cover it with a very thin aluminium layer. This is to protect it actually from oxidation, or let's say crep on the surface. So here is a set of devices. So we start by just changing the lower bottom of these squids, going from also a die-end bridge as on the top, just so a bow tie type of constriction, and we move to longer constrictions. Actually, these were the first device fabrications. Now the resolution and quality is even better by tuning the process. But that's the basic idea. So we can really play around and see what the superconducting properties of these devices are. And indeed, if we can control the kinetic inductance of these nanobridges. So if you summarize these ingredients, you can neglect the geometrical inductance, you can do a small calculation, you get these two simple equations, which are combined, let's say, and they give you, let's say, for the zeroth vorticity state, which is marked in blue, this dependence of the critical current on the magnetic field. One can do that very simply, but the idea is that this slope will give you the insights on the current phase relationship of the nanobridge, while this slope tells you about the bow tie structure. The nice thing here is, compared to standard aluminium squids, you have very nice straight lines which are directly related to the fact that you have a linear current phase relationship. So this should be directly an evidence that indeed you have a linear current phase relationship. Keeping in mind, let's say, the coherence length in the molybdenum germanium, which we measured through a field dependence, you have a coherence length of 10 nanometer, which is much more than the device geometry. You actually expect this linear current phase relationship. So that's the idea, and then we plotted the dashed lines here. This is for the -1 vorticity state, the 1 vorticity state. So the only thing is it's just shifted, and that's all. Of course, this shift, and this also shows, and I think we show it as well in, not I think, we show in our results, why we select molybdenum germanium. It is a high, let's say, resistive material, so it's interesting for quantum phase slips. So this is also ongoing efforts we try. And also it has a very high, so the lambda is very big, which makes that actually you don't see any field modulation along the axis. So you just have a shift of this dependence of the critical current as a function of field with vorticity. And this goes on actually very far. Okay, and that's it. So these are the ingredients. So then, of course, one has to measure them. It's in a 300 millikelvin setup. I just show here, not to show the setup. I think it's just a conventional heliox system. But I think what is important is we go from minus currents to positive currents or vice versa. This is important in the experiment. We have heating present in these systems. And this is something which is always present and we have to take into account, which is obvious to some extent, but we have to take into account if we want to understand the devices. Also, there is, of course, stochasticity related to the phase slip events which are present, and therefore, as shown here, one has to do 10,000 of experiments to get the critical current distribution. So we don't do just one IV measurement, we do a lot, just to get the statistics right. But at the end, I don't discuss today, but this is just how the critical current is determined. Okay, so this is the experiment, 300 millikelvin, and indeed we see if we put these vorticity diamonds onto it, we indeed see a very nice linear phase relationship. It is shifted for different vorticities. Of course, we lack a lot of points on this diamond, but that is related to the experimental principle, which I will try to explain you later. But indeed, we can nicely fit it. We have a linear phase relationship, and so we can even get the numbers. So we can determine the kinetic inductance. And for example, in this case, for the nanobridge, it was 261 picohenry, sorry. So this is a very direct measurement of the linear current phase relationship. So let's try to use this technique as a function of devices. So these were the devices I showed in the beginning. We changed from a symmetric nanobridge, so a bow tie at the bottom, and we start elongating the bottom one. And what we nicely see is by changing the length, we change the kinetic inductance. This is into the formula. And this is nicely seen. So we have a control. So this is dependent by the ratio of L, the length divided by the width. We can nicely control the kinetic inductance. Of course, how nice you can control the kinetic inductance as a function of these parameters definitely depends as well on sample quality. But this gives us really a degree of freedom to change, let's say, the kinetic inductance. So I think we can control, we can measure the kinetic inductance. And we, of course, see a nice dependence which is controlled, and moreover, actually we also repeated for several devices. This is really reproducible. If you do it for 5 devices, the numbers are very close. So here we did on exactly the same sample just to get a bit of insights on the dynamics. I'm not sure if it's very well seen, but the device which we asked to the group of Antwerp for exactly the same dimensions, try to model this using time-dependent Ginzburg lambda. So they started, as shown here, at the vorticity state of 1. You cross here the vorticity diamond. You indeed generate a phase slip, and this, of course, depends on which branch you're leaving. Then you have a change of the vorticity state going to -2. in the time-dependent Ginsburg-Landau, they can easily define, or let's say determine, the vorticity state. And then you go to the zero vorticity state, so there is a jump to the zero vorticity state. You can increase your current, and then here happens, let's say, a transition to the normal state. And this is important. I mean, let's say we can nicely model the device using really the correct input parameters. But I think the main takeaway, because these simulations are very dependent on small things, so you can always, I think, get the, let's say, insights. But what is important is that in the time-dependent Ginsburg-Landau, you can clearly define exactly which phase jump is happening. So which vorticity jump is happening, which is, of course, what we call in the experiment, it's a hidden phase slip line, because it causes a very abrupt jump in the voltage, which is indetectable in the experiment, or you really have to go to very high time resolution experiments. So, and that's why we call them hidden. They are there, but we cannot observe them, and this, again, is important. So they did it as well as a function of field, so they nicely correspond, let's say, the linear current phase relationship, a bit of rounding at the top of the diamond, but this is because time-dependent Ginsburg-Landau also takes into account the depletion of the condensate due to current. So this is not taken into account in our simple model. But so what is very important is that one can include, but in these simulations we did not include heating, which is an important ingredient. And the state preparation is just introduced in the model by just adding fluctuations, doing a zero field cooling, and then you end up with a certain vorticity state to start. You then deterministically scan the IV and see the observed vorticity state changes. So, and that is different, of course, but I think it already grabs the experiments. So this is, let's now come back. So why we see these kind of currents, critical currents, as we measure as a function of field. So to come back to that, let's say, just remind, we started here, so we do an IV sweep, we start at negative current values, and we sweep the current up. That is how the experiment goes. So the first observation, of course, is you only see the tip of the iceberg, which is a pity, because it would be nice for a better resolution to also measure the vorticity, let's say, vorticity diamond here at lower fields. But as stated before, if we want to observe this transition, we should have a highly time-resolved experiment. It's possible, it's not, but I think it's a challenge. So I think there are easier ways to try so. So why do we observe the specific vorticity states? And I think one ingredient which you have to take into account is, of course, the energy of the vorticity states. And obviously this energy of the vorticity states depends on the magnetic field, as shown here. So the zero vorticity states has the lowest energy at zero, and then it goes, like, depending on the applied field, related to the flux quantum. So this is really important, because it means at zero field, the zero vorticity state is definitely the lowest. So, while if you take into account here, in our case, for example, at 3.4 millitesla, the first vorticity state becomes the lowest. So, and this is important because this will rule, let's say, the freezing process. You will always freeze in, or at least to a very high percentage, into the lowest energy state. Let's now go back to one measurement, just to understand one measurement, and then if you understood how one measurement comes alive, you actually also understand the dependence on field. So let's take here this value at 2 millitesla. What we see is we do an IV sweep from negative currents to positive currents, and we observe the zero state, so the critical current related to the zero vorticity state, and sometimes the one vorticity state. So, and the question is, okay, why? And so we have to take into account, and this is important, if we do these experiments, we have heating. So actually the freezing of the state, so the state initialization happens here. Roughly at, this is the retrapping current, roughly at, let's say, 10 microamps, so here. The question is, what state do we initialize? Most probably the lowest energy state, but this is something we have no idea. We only have the end product of the initialization state, and then we increase the current, and the question is, perhaps we are in the zero state, we cross zero, go to 1, and then finally measure 1. The problem is we have no idea. There are too many variables. So this is just to show you, at least directly show, so we plot energy and the probability of finding a state, which directly shows that actually the lowest energy states are definitely the most favorable states, the one you measure the most, which to some extent is already makes sense. But okay, so let's now try to tackle what the final product determines. And to do that, we want to make the experiment more simple. So we want to really know, and I think that's the crucial ingredient, because we have no control on the cooling process, we want to really know where we start at zero current. So how we do that is given as well by the group of Bezriadin, is a state preparation process which actually uses the fact that at certain field values only one state can survive. This is a bit more tricky than this, but that's the idea. So for example, here at these fields, only zero, let's say, has a critical current. If you're, for example, in the vorticity state 1, you would be here, you would simply go to the normal state. That's the idea. So it's like you park your car, and this is the principle. You park your car, but you need a system, let's say, which checks is the car parked on the right spot or not. If it's not on the right spot, you just have to get outside the parking lot, and then you have to try again. So this is the idea. So experimentally, it is very simple. We increase the current exactly at this field value. We increase the current until we are at this region. There we stop. And then only if we are, and this is the selection criteria, the one who checks if your car is parked properly. Here you will check, is it the zero state or not? If it's not the zero state, you will simply go to the normal state, you do again a field cooling, and you start all over again. So you try a second attempt, and this is how you do it. If you do this enough times, you will end up with 100% certainty in the zero vorticity state. As stated, you can do this for all states. You can do this for the one state, but just at different field values. So just select, because of course, as you see, for the one state, you have this region, but you just have to change the field. And so now you have control on the starting process. And this is now the experiment when we start really always at the zero vorticity state. And you nicely see there is a region, if you, in field here, if you start with the zero vorticity state, you end up reading out the zero vorticity state, which of course makes sense. But obviously, there is also a region where you start with the zero vorticity state, but you measure the one vorticity state. And now you finally know that you observe the hidden phase slip, meaning that when you cross the zero vorticity state diamond, it has to jump to 1. And then, of course, afterwards, in your experiment, you will measure the one vorticity state. So you really now have control across the full process, because you know where you start, you know where you end, so you know which transition has to be appeared. So we can compare that, and there is a clear difference. Just keeping track of time. So there is a clear difference. So this is the conventional, what everyone does. No? You start with a negative current, you go to a positive current, and this if you do a state preparation. State preparation, in this case, the zero vorticity state. So of course, again, you measure zero vorticity state here at low fields because it's the lowest energy, and you start with that. But you nicely see actually that when you go high enough in field, you have these jumps, and it means like if you're high enough in field, you go here, you have a jump, a hidden phase slip, and then you actually detect, for example, in this case, the second vorticity state. Nice thing is what we don't observe, and this is already, I think, an insight, is you never observe, or almost none, a 1. So one single phase slip is not occurring in these experiments. And so this is, I think, something which is also seen in other devices. Moreover, there is an asymmetry from left to right, and this is related because the phase dynamics, depending if you're at the left or the right side of your vorticity diamond, happens in the nanobridge or in the constriction. Obviously, these are two different entities, so one expects also different jumps happening at the left and the right side of the vorticity state. So we said the tip of the iceberg, we cannot measure this one, but we can use this jumping of vorticity states when you cross the border. And so what we do now is we start in 0. When we run here, and with the student we tried, you can do this for 24 hours, you remain in the zero vorticity state. So it is extremely stable. So if you then read out, so we prepare in the zero vorticity state, we go here, so we remain in the zero vorticity state, we read out, and we read out the zero vorticity state. But from the moment we cross this barrier, we do a jump, we come back, and this is not a reversible process. And so what happens is that at some cases, for example here, you will jump, in this case, you will jump to the second state, you measure, and you will have a probability of not measuring the zero vorticity state. And this is then the process which is explained, but I think it's too technical and goes in deep, but that's the idea. The jump is irreversible. And so the idea is if you mark the onset where you're not 100, sorry, where you're not 100% jumping to the zero vorticity state is marked by these lines, and you can really see now the vorticity diamond in the complete field range. So you see these hidden phase slips in a clever way, not because we can measure them, but at least we can pinpoint because of the final outcome of the experiment. So okay, then actually we tried to build a memory in the same spirit of the group of Bezriadin. What you need is, so they have niobium squids, so it's niobium, and then there are here very small weak links. We thought we can, due to the nature of our fabrication process, do it more controlled. We have a long nanobridge. Why? Because then we have a very big critical phase angle, which actually means that the diamonds are very flat. So it actually means, as shown here, so we can do, again, the critical current measurement. So we have very flat diamonds if we elongate the bridge. So it means that the vorticity state survives at very high fields, and you can acquire a lot of phase changes. So we have a lot of states. So in this case, we do the calculation, we do the fitting. At zero field, we have 17 states available. So you have like a multi-level memory element. So it was nice to store information, but I think also nice, I didn't discuss here, is also the energy of the states, as shown before, and it's of course natural at zero field, is different. So you can prepare a state, for example, state 2, which is the highest, is very high in energy, and you can use it as a sensor. A single photon detected by your squid will lower the energy of the state, and you can do a readout afterwards. It's a bit similar as a single photon detector. But okay, can we do that? So that's the question now. And we use the principle of before. We have a state preparation protocol with field. We can write all the states, and this is what we believe. No, we can prepare in every vorticity state of the 17 states, and then we go to zero and we read out. And so this is the result. So indeed, you can clearly define which state you are, going from the 2, 1, 0. So we have actually, in this case, 8 states, which are, so we have a memory where we can store information in 8 states. Be aware, for the preparation, we need magnetic field, but I think this was also like in the work of Giassotto, which I showed in the beginning. But so this is the critical bottleneck, I think, is that it would be nice, of course, to do this at zero field, so we don't have any field needed or no coils, additional coils to get the memory running, and this is on our to-do list. But so it really shows why we don't see all these lower states. Yeah, this is very simple, because for these states, you will have a hidden phase slip. So you will, so for example, if you prepared in state number 8, you are at very low current, so very low heat. You will have a hidden phase slip going to one of these states here, and you will not be able to distinguish between that state. So only the state, so heating in these devices, to some aspect, it's like with the single photon detectors, is a bonus. It's needed to be able to read out these states. So, okay, I think to summarize and to stop before 1, is we can measure and control the kinetic inductance. We can actually identify, because we have this protocol, we can read the initial states, we can define, the initial state, read out the final state. We can really explore phase dynamics without the need of fast experiments. And we gain these insights to create a superconducting memory. So this last is a work in progress. So what to do now, as stated before, is we are now building, or no, this is done, is so high frequency experiments, and to add our resonators and combine them with these type of squids. And the nice thing is, because compared to one of the speakers also today, is, I mean, control of the qubit energy would be really nice. So here we have the ambition to bias actually the squid and try to change, let's say, the resonance frequency from that perspective. That's it. I have to thank you for your attention, and I'm open for questions.
Thank you very much, and we have time for questions, comments.
Thank you. I have the following problem. Please help me to relate this notion of a hidden phase slip to a common notion which has been used in this field already a long time, a phase slip. A phase slip has 2 features. It's an event where in some part of a superconductor there is no uniquely defined phase. And second, it's a topological defect. It's always linked to suppression
Mhm.
Are these two constituents of a common definition of a phase sleep present in the hidden phase sleep? Or we should simply take this new definition as such? Thank you.
No, so it is a phase slip as you define it. It's hidden for the experimentalist in the sense that we cannot measure it, so we cannot detect it. Of course, as stated, we could, because what are the properties? It's a very sharp jump in the voltage. If so, it is hidden, yeah, for me, in the perspective of doing DC measurements. So it's hidden if you just do standard characterization of a squid, but it's not hidden if you would do time resolved measurements with enough speed. It should be present. So from that perspective, it's hidden, but it's a phase slip event. Yeah.
Yeah, question. There was usage of time-dependent Ginzburg-Landau equations to simulate motion of phase slips, right?
Yep.
So, is there any attempt to use more fundamental approach as by usage of Ginzburg, Bogoliov-Dijon theory?
No. At this moment, there is no, let's say, but I think it's also very difficult due to the size of the device. But at this moment, there is not, because at the end, the physics is grabbed by this very simple model, and we don't have the ambition to really, I think also the physics is settled of this weakling. So I think we don't get more insights. I think it becomes important, this type of more extended, if you are really interested in the microscopic physics of the weakling, which in our case is just a wire. It's a very simple case.
Well, just the dynamics of quasi-particles can tell us a lot about how the system approaches equilibrium, and also can give us the insight into possible, eigenenergies and things like that. I mean.
Yeah, no, but I think anyway, perhaps it was a negative response. I think if someone can do that for us, it would be great. And if we can learn from these simulations, I think definitely we have, certainly as well with the spectroscopy kicking in, I think we can do much more related to really the states and the dynamics in these devices. So I think it is worth to, at this moment, we haven't done it because we don't do it, so we need a partner. That's the idea.
Thank you.
Yeah.
So I have a question. So this transition vorticity, they are two phases. They are first order transitions. I wonder if you can get like a latent hit of those transitions, or I mean, is there a way like from the reversibility? I guess you see what I mean? I mean, probably you can go like sort of superheating state, and then supercooling, and perhaps from that size you can get. But I don't know if you see that, or I'm completely missing the target here.
No, I think the process itself now at the moment is not studied. We just see the end product. But I think, for example, if one be able to measure, let's say, locally temperature, I think that would be an interesting while going through this transition. This I agree. But now we just see, we know there is a phase slip. We actually know where it, let's say, where it happens. But with the phase slip event itself, we don't explore at all. Yeah. But I think indeed it's an interesting question to see this transition and how it behaves. But then perhaps we need
we'll discuss
a temperature sensor with a very high resolution, which I think was presented before me. Okay.
So I think that time is over, and also the session is over. So let's thank all speakers again.
Oh, great. Thank you.
Okay. Okay, thank you very much. And so thank you, the chairman. And of course, I would like to thank also the organizer, which to give me the opportunity to present this talk. So I work in Dresden, and however, and I'm going to speak about an example of parity time symmetry breaking, such as the dynamic vortex-mode transition, but I will use this as an example to show that architectures, even with the same element, if carefully designed, can lead to interesting broken states. So, and then so the question will be, what can we expect theoretically of time broken states from, for example, a twisted cuprate heterostructures, which is what I'm working right now. And also I will explain why these heterostructures are so difficult to make, and specifically the problem of the oxygen. I will show our measurement of the Josephson coupling between the twisted cuprate heterostructure. I will show that we have detected second harmonic modulation at very high temperature and specific angle, and also discuss some work in progress about the detection of the topological state. And also I will finally discuss the possibility to integrate this heterostructure in hybrid superconducting and thermal circuit with the exotic mechanical electronic properties of this actual heterostructure. Okay, yeah. So first of all, I would like to thank my group that made these works possible so far, and the collaborators which range from a very different of institutes, from Dresden, Cornelius Nitsch, Valerio Vinocu from Terra Quantum, from the University of Napoli, Domenico Montemuro, Francesco Tafuri, Valentina Brosco from Rome, Uri Voli from the Max Planck, Genda Guk from the Brookhaven National Laboratory, Kenji Watanabe and Takashi Taniguchi from NIMS, Philip Kim from Harvard University, and Pavel Volkov from Rutgers University. And special thanks also for some technicians that helped me a lot during this work. So first of all, an example of an architecture where you could see a dynamic broken states of the parity time symmetry is an array of superconducting islands on top of gold. So you can realize thousands and thousands of superconducting islands. You have proximity effects in a square array lattice structures. And what happens is when you apply a magnetic field that you create a Josephson vortex. You create a Josephson vortex, which of course has some sort of directionality, so chirality. And this Josephson vortex will fill all the gap in this square array. So depending on the magnetic field, you may fill as many Josephson vortices for each plaquette in your system. For example, in the case of filling factor 1, so basically means one Josephson vortex for plaquette, you can then apply a current through your superconducting electrodes in the array, and then you can switch a vortex multi-insulating state, so basically a frozen square array, very precise square array of Josephson vortices, to a dynamic response of the Josephson array in a vortex metal. Then if you do the scaling analysis, you discover that this kind of transition, which is a dynamic transition because you are applying a magnetic field and driving the vortex lattice with a current without any kind of thermal creep, because you are below the threshold of where a thermal creep can happen of the vortex lattice, then you see that the exponents belongs to the Mott class, or liquid glass transition class, universality class. And then the dynamic mode transition has been identified as a PT symmetry breaking phase transition, given to the non-equilibrium nature of the system. And this experiment has been reproduced very recently, and using a different array structure. And in triangular structure, you do see exactly the same thing. Okay, now, so you can, by just playing with the architecture, you can realize time-broken states. So I didn't change, I just used niobium. So I didn't use, I just niobium. But I organized niobium in a special way, and I saw some spontaneous time parity broken state. Now, There has been a lot of work, very long, but the trick was that I get rid of the detrimental disorder by some fabrication technique. So the disorder, how you control disorder, is very important. And this is very important also for twisted architecture of cuprate structures. And there has been many, many theoretical proposals that have discussed the inhibition of node-to-node quasi-particle tunneling at finite twist angle, because you have these nodal gap structures, and in this nodal gap structure, you can basically play a little bit to suppress the quasi-particle tunneling, given that you select some specific angle. Now, the fact that you have a D-wave superconductor is known in these cuprate structures by a variety of techniques: spectroscopy, scanning tunneling, thermodynamics, and so on and so forth. And more recently, some theoretical proposals suggested that at some specific angle in this vertical heterostructure, so along the z-axis, in this vertical heterostructure, topological protected superconducting state at very high temperature may arise. And a spontaneous and dynamic time reversal broken states at matching angle can be detected. So spontaneously or dynamically. So for example, at some angle, you may expect a dynamic broken state. At some other angle, a spontaneous broken state. So this means practically from an experimental point of view, if you just stack two flakes on top of each other, you give an angle, and you don't do anything else, you may get a spontaneous broken state. Instead, if you stack just two flakes at some other angle, and you apply a current, you may deplete enough particles from the nodes such that you open a gap, and then you have a topological state. So in that case, it's a dynamical broken of the symmetry. So you put a die-wave superconductor on top of another die-wave superconductor, you get a special order parameter with an imaginary component. You can realize a phase diagram, and then you discover that this, in the current phase relationship, the current phase relation become different in a range of angle that is different than the others. So for example, in this case, close to 45-degree angle with some sort of uncertainty, okay, by the theory, for several reasons. That if you want to make questions, I will reply. Now, what this experiment has been done on the vertical axis, because this experiment has been going for a long time, and people have realized also in plane Josephson junction using grain boundary junctions. In that case, the C, so the coherence length in plane, is around 2 nanometers for the cuprates. So you are forgiven if your sample has some imperfection, like as much as when you realize aluminum oxide junctions. But in the case of the vertical junction, you have 0.1 nanometer coherence length, so basically 1 angstrom. So if you get an imperfection on your crystal of 1 angstrom, so one atom moves just a tiny bit, then you have destroyed the coherence of the superconducting state across the layer. In fact, people have been not measuring the wave superconductivity across the layers in the z-axis, and they realized a main experiment where if they measure the JC as a function of the angle, the JC is more or less constant, except only in the case of the Whisker cross junction, where do see some dependence as a function of the angle, but that was not a true D-wave dependence, had some sort of large, let's say, discrepancy. In fact, if you, also more recently in Shanghai, an experiment on thin flake show, again, no angular dependence. So one of the things that is in common about all these experiments is that after they stack the bulk crystal or the thin flake on top of each other, they anneal the flake at very high temperature in order to restore superconductivity and the oxygen at the interface. And this means that they had to restore the superconductivity by reintroducing the oxygen. So they apply very, very, very high temperature. But people generally, I come from a material science X-ray radiation community, so I know how much oxygens are sensitive, how much oxygen interstitials and oxygen defects have a real and k-space order. Generally, people call them oxygen ion conductor, and has been works in the past showing that the disposition of the oxygen order in this material is really important and beneficial for the superconducting characteristics. In fact, oxygen is a very light element and is one of the most vagabond of the elements. So it's very difficult to keep it in place. So when you grow your crystal, generally the crystal grows and put the figs naturally where they should be. But as soon as you start to touch these crystals, then you don't know anymore what you're doing, basically, because of the oxygen extreme sensitivity. Oxygen, in fact, in some cuprates have formed real and K-space orders which are strongly correlated with the high temperature superconducting property of the system and form stripe structures across the rock salt layer that you can detect with X-rays as peak and map on top of your sample. It turns out that if you want to change this K-space order, you can irradiate your crystal structure with X-rays, but you can start then to move the oxygen and cluster them together in kind of ordered structure only if you are around the temperature where the oxygen are mobile, which is between 200 Kelvin and 300 Kelvin. And this is shown here. So we apply X-ray fluence, we have an intensity, there is a threshold time, and at some point these oxygen puddles start to basically increase. This is an X-ray peak, which is increasing as a function of time. And then if you quench immediately your crystal temperature, you get superconductivity that is depending as a function of the K-space order of your oxygen. So this means that if the temperature is very important, and what you do at which temperature is very important when you process this material. And so the BISCO structure, when you try to thin down, it becomes insulated. This has been shown by Novoselov in 2005 when stamping it with a Scotch tape on top of a substrate. He was able to isolate thin flake of BISCO, but they were pretty insulated. Recently, with my work and the work of a group in Shanghai, we were able to isolate high temperature superconducting thin flake and measure the high temperature superconductivity in a well kind of reproducible way. You can realize structures, devices, and so on and so forth. However, then it turns out that it's very incredible because generally high temperature superconductor, when you decrease the thickness, also they decrease the superconducting critical temperature. It's very difficult to have 1 nanometer or 2, 3 nanometer high temperature superconductor which have the same bulk TC. But for the BISCO, it's possible. In fact, if you look at by X-rays with 100 nanometer X-ray beam at the Bucharest National Lab, we scan and we map the crystal structure of the system. It basically shows, sorry, this is a little bit, it shows basically that the variation of the K-space order on the thin flake respect to the bulk states, it's only of 0.001. And so it's a reciprocal lattice unit. So it's just a Gaussian. So this means that this incommensurate lattice modulation that is typical of the BISCO structure remains basically almost intact when you thin down the crystal down to this level, okay? And now, how do we, this is a material that is clearly sensitive to air, so to water molecules, but is also sensitive to all the possible polymers or solvent that you're going to use in order to realize any possible fabrication, which is the typical standard method that people in the clean room use to realize nano devices. So you have to really go beyond any state-of-the-art known fabrication technique to deal with this material. So I developed a new technique that is based on this sensitivity of the oxygens by taking in consideration the following thing. The oxygen RK configuration must be frozen below 200 Kelvin during the BISCO interface formation. And the lattice of the BISCO crystallinity must be preserved against any reaction with water molecules. In fact, you have, even at very low vacuum, you keep having water molecule eating the surface. And this water molecule will react with an oxide, no matter what you do. They will diffuse and they will detach. Now, this is a kind of also a lucky discovery, because at the beginning I was not sure about that, but it turns out that the PDMS, EPDMS is a polymer, okay? It's a kind of, it's not a regular polymer, it's a siliconate polymer in some sense. And the PDMS become basically like a scotch tape when it's close to this glass transition temperature. Generally, when people stack graphene, TMDCs, all these other 2D materials, they use polyacton polymer like PC or PPC, and these polymers have a glass transition in which they melt. So when by melting, they basically surround your crystal, and by refrozing them again, then you can pick up your crystal. But this transition, when they melt, appears around 200 Celsius, at very, very high temperature, which is completely intolerable for the BISCO, at least from my point of view, okay? And then, however, the PDMS has the special property that this kind of glass transition occurs at minus 123 Celsius. So counterintuitively, the PDMS becomes basically more liquidish, okay, the more you go low in temperature, okay? Of course, it's still a solid. It's just a very tiny kind of soft behavior. And so it turns out that you can have a BISCO, you can use the PDMS, you lower in an inert atmosphere the temperature to a minus 100 Celsius about, you can tear apart two flakes. In less than 1 minute, you restack them on top of each other using some robot that we have built. You choose the angle, and if you do all this, then you release your flake at minus 30 Celsius, the PDMS become less sticky, and then you have a perfect transfer technique. Then you use shadow mask evaporation with some evaporator in your integrated with your inert environment, and you can realize electrical contact. Now, if you are rich, you can have an ultra-high vacuum system. I have a high vacuum system. So I had to figure out, in a high vacuum system, you still have water molecules, even if you have 10 minus 7, okay? So, and the water molecule can already make a difference. So for example, this tells you how challenging it is to realize cuprates devices. So the superconducting TC is 90 Kelvin. Perfect. So if you say, okay, I see this, I publish. Great, I made an heterostructure, 90 Kelvin. But the point is that these systems, which is not encapsulated, is very different from this system in terms of Jobson characteristic. You will see the Jobson junction in both systems, but the Jobson characteristic here is 1.2 kilooampere per centimeter square in intrinsic, the intrinsic bulk junction. But if you use the other characteristic, the other sample with no encapsulation, because you didn't have an ultra-high vacuum system, okay, then the water molecule will degrade your system, and you will have a much decreased critical current density. We just published this now for the moment in arXiv, but whatever. So, an example. So, for example, we made many samples. So you have a cryogenic transfer, pure encapsulation, pure evaporation, high vacuum. You get all the same kind of superconducting critical temperature. You do see the dynamic resistance, the very strong coherence peak, and a hysterectic behavior. The same happens if you have a cryogenic transfers, pure evaporation in ultra-high vacuum. You see many, 24 samples here. We made some statistics. We have a sigma of 2.9 Kelvin in terms of TC, and a strong hysteretic behavior as well. Okay, this is just to make a panoramic, but this is just to give you a glance of what I'm going to say in the next slide. So you see the critical current of this sample. As soon as then you see that it's the same scale, it starts to become lower. And this is a function of the angle, okay? And so you have to imagine this as flake that are twisted to some extent, or twisted with some encapsulating boron-nitride structure on top. And then it turns out that you start to see some D-wave angular dependence already from the raw data, okay? Which you see better here. You see here the D-wave angular dependence that goes basically, that change the critical current of about 2 orders of magnitude, more than 2 orders of magnitude, down to 45 degrees, where you have the node suppression, and rise again. And the same happens for the other method with the encapsulation, where we do see basically the critical current decreasing, as you may expect in a D-wave vertical junction. Also, the temperature for a 45-degree junction tells a lot. Of course, temp cannot tell all. For example, I cannot see light oxygen elements. So when you see a temperature, right, it's very nice, but where are the oxygen, right? So you can see this, but my sample can be insulating, okay? So this is the problem of this material. So, but anyway, this is nice and unprecedented, the quality. So you can see the D wave, the superlattice incommensurate structure modulation that is appearing exactly at the interface where I have exfoliated and restacked the sample. So these are the bismuth, the strontium, the copper, and the calcium atom, oxygen. No. Now, another aspect that is interesting of this twisted nodal structure is that you have a nodal superconductivity. And this is very special because people remember that high-temperature superconductors are high-temperature superconductors. So thermal effects start to play a very important role in the nodal structure. So what you see here is the ICRN is not simply going like in the Ambegogar theory, like decreasing as a function of temperature, but is having some non-monotonic effect. This non-monotonic effect depends strongly on the angle, so it's peaking around the, let's say, intermediate angle and returning back to the normal, let's say, decrease of Ambegogar around 45. And this is given by the fact, I can explain you later, but it's basically given by the depletion by thermal fluctuation of Cooper pairs by small gap and big gap, depending on which side you are, if you are in the node, in the antinode, or if you are in the node. So basically, you are depleting, and this depends also on the phase. So because this is, you have seen here phase, nodes, and antinodes. So you have to make some subtraction plus, and this is explained by theory, can be explained by theory. And also you see the non-monotonic dependent in the Shapiro steps, which we measured 70 gigas in the junction. So this kind of behavior is also seen in the Shapiro steps. And the Fraunhofer pattern at a low angle, let's say a 42-degree angle, a 41-degree angle, see a normal, a normal shape, as you expect, of an intrinsic Josephson junction. And the the Shapiro step at 70 gigas show integer filling, like you expect in a reasonable Josephson junction. So what you could say here is that you have first harmonic modulation of the current phase relationship. So it's a Josephson junction, okay? Now, if you instead get the angle close to 45 degrees, what happens, this is especially a 44.9, what happens is that you start to see many more oscillations in the Fraunhofer pattern, some asymmetry in the Fraunhofer pattern, which I don't know if you can appreciate, but this has some deep meaning, okay? And then fractional or half-period Shapiro steps that you can see in this kind of fume that you see in the 2D color plot, okay? So now, if you have, how much time do I have? Okay, so I finished. So I just want to say that we are doing some work in order to characterize this possible topological state. This is not a proof of topological state, but it is a strong indication, given that I did whatever I could to remove the possibility that there is some disorder at the interface. Because second harmonic can easily arise because of disorder, but I have, if you want to ask me more, I can show you why we believe that is not. And we have other evidence that I don't show here that show definitely that is not, and that we have a topological state at this temperature. But for the moment, this is enough. And so for the future, what we want to realize is complex circuit. So now for the moment, I just make 4 contacts on top of each flake, and that's very simple. But what we want to do is a complex circuit that can be fabricated at the interface of twisted heterostructure. This requires a completely new technology that we are now developing. We're using membrane, so we realize thousands of circuits. We stamp them at cryogenic temperature. We bond them. And then we can realize even solution of 150 nanometer to realize possibly superconducting resonator and so forth. And we have shown that we can stack this membrane. We have this via contact that perfectly touch at minus 90 Kelvin the flake, so we don't use any polymer, no solvent, no temperature, nothing, okay? And we can measure 91 Kelvin exactly like you expect in a bulk thin flake. And you can see the whole anomaly, and this I'm not going to discuss very much, the whole anomaly by the sign reversal change, which is a typical feature of the cuprate structure. So this opens the possibility to go in hybrid superconducting circuit that Davide was speaking about before, and also for this very sensitive heterostructure. So Okay, so this is just some schematics of what we have in mind, but so basically with this I would like to thank you very much for your attention.
Could you possibly have a way of detecting an S-wave component in the order parameter?
Okay, so if you see, it's a matter of, okay, it's a question that I thought a lot about. And so this is not zero, okay? So there is a finite resistance here. Theoretically, what you would expect in a D-wave superconductor is that goes to zero. Right? Now you have two interpretations for this. That you have a S-wave little component arising in this part, or you have co-pair tunnel tunneling. Okay? So these are two Cooper pairs that tunneling at the same time. Now, so on data that I don't show, I believe the second option that is the case, but the question is fair, and from what you have seen, you cannot rule out, but from what I will show in the future, you can rule out.
Okay, I can just cite that there is an old experiment by Müller and Keller who claimed that there was an S-wave component in 3D materials, but not in 2D. So if you put a second flake, you should look at what is happening, maybe.
I agree. I understand. This has been a very long standing discussion. To my opinion, I'm more interested also in this discussion. For me, it's interesting, but not so interesting. And I explain you why. Because at the end, what I really want to do is hybrid superconducting circuit. And for me, I need a way to have the highest DC with the lowest critical current, trying to avoid as much as possible disorder, so that I have the purest Johnson junction I can imagine. So I don't want to too much discuss about this, but definitely what my data show is that from no angular dependence at all, there is now a strong of spanning two angular dependence that you could at least say D-wave-like. Okay.
Okay, are there further questions? Please, you were. No, please.
Thank you. So thank you for the talk. It was fantastic. Is there a specific signature of the topological superconducting state on the Fraunhofer physics?
Well, I think so. I think so. But this is because I mean I don't want to say something wrong. Okay. But in my opinion, oh man, so it worked so far. We managed.
Don't worry.
Okay. So, I mean, if you have a good eye, okay, you could see that this lobe, right, on this side are losing the steps on the other side. So there are a little bit of asymmetry from the two sides, from the IC plus and IC minus, like you showed in your, I know.
This was my question.
I know, but since this from here is not so evident, I didn't want to make a big deal out of it. But I have other data that shows that is much more evident.
Thank you very much.
Okay. I think we have no time, and I invite my co-chair, Joris van der Bonden, to give a certificate.
It's the certificate. Thank you very much. Thank you very much. Thank you very much. Oh, sorry.
Your pocket.
Good afternoon. I hope you hear me and you see my screen, right? Yeah, I see that. Good afternoon, dear participants. I would like to present my work, oscillation, chaos, and ordering of the vortex motion in superconducting nanotubes under modulated transfer current. we study superconductor open nanotubes with a small slit. Along this slit, we have contacts, and transport current comes in and comes out from these contacts, and we measure the induced voltage on these contacts. Usually we take niobium nanotubes with 5 micrometer length from 200 to 400 nanometers radius, and 50, 60 nanometer thickness. Also, an hour ago, Professor Fomin had a presentation where he discussed that such structures, if they are exposed in an external magnetic field, there may be different regimes of their work. For example, there we can see vortices or phase slips. In this talk, I would like to focus on vortices which appear in such structures, and I would like to discuss several interesting effects which appear in such structures and associated with vortices, and what happens if we modulate a transport current with a small alternating component. First of all, vortices are nucleating at one side. They are moving along the nanotube and denucleates on the other side. We know that this generates induced voltage, and since vortices are nucleating and denucleating and they move non-uniformly, the induced voltage is not a constant value, but it deviates with time around its average value. And as Professor Fomin has already said, there are two characteristic times. The first time is the time of light, delta T1, and the second time is the period of the nucleation, delta T2, and surely they depend on the magnetic field, the external magnetic field, and on the transport current. However, we can find such value of the magnetic field that the denucleation happens, for example, at the same time as the nucleation happens in the same half cylinder on the other side, or vice versa. We can find such value of the magnetic fields that the denucleation happens between two nucleations of the vortex. In the first case, we can expect that we know that the average number of vortices is more or less the same, and in the second case, the number of the vortices and an average number of vortices, it oscillates with time, and in this case, we can expect that the voltage oscillations are higher as well. It means that if we plot the standard deviation of the induced voltage as a function of the magnetic field, we can expect some oscillations in the amplitude of this alternating component itself. And if we model our nanotubes with time-dependent Ginzburg-Landau equations, we see that oscillations do appear and these oscillations have a fixed period in some regions of the plot, and it means that the ratio delta T1 over delta T2 is a linear function of the magnetic field in this interval, which can be expected from the general theory. And an important tool that we use here is the spectrum of the voltage signal, and we calculate it numerically, but however, we can expect that such spectra can be obtained in experiment. And we have several interesting moments here. First of all, we have a main harmonic in the spectrum, which is plotted as a function of the magnetic field, of the external magnetic field. This main harmonic is associated with the period of the nucleation of our vortices. With green arrows point to the higher harmonics, and they are associated with the main harmonic because our system is nonlinear. However, we have at some point of the magnetic field we have fractional harmonics and region of the chaos. These fractional harmonics are, for example, a half of the main harmonic or 1/3 or 2/3 and so on. And our question is, why does these fractional harmonics appear? To answer this question, we draw the trajectories of the vortex motion. And for example, if there's no fractional harmonic, there's only one path, one trajectory in each half cylinder. For example, this is the upper left panel. If we see the harmonic associated with 1/3 of the main harmonic, then there are 3 paths in each half cylinder. It is the bottom left panel, and this means that fractional harmonics appear due to the splitting of the trajectories. And for example, it happens then the first vortex, then it nucleates, it chooses the first path, the second vortex chooses the second path, the third vortex chooses the third path, and then again the fourth vortex chooses the first path, and so on. If we take a smaller nanotube, for example, our previous effect, our previous slides were done for the nanotube with radius equal to 390 nanometers, and we had a chaos, we had fractional harmonics. In the case of the smaller nanotube, with a radius equal to 240 nanometers, we don't have fractional harmonics at the same values of the magnetic field, and we don't have regions with chaotic behavior, as we can see on the left panel. And this appears due to the fact that our vortices are confined in a smaller region of the nanotube, and it has no freedom to move left or right as much as it had in larger nanotubes. And however, in this case, if we take smaller nanotubes, we can see the effect of steps and frequency lines. It means that at some value of the magnetic field, the frequency changes with a step. if we studied why does it happen, and it appears due to a stronger interaction between vortices from one half cylinder with vortices from the another half cylinder. So it creates stronger correlation between vortex motion. Okay, and now we want to add a small modulation to the transport current density. It means that we add a small alternating component to the transport current. In this case, the amplitude of the alternating component is 30 times smaller than the direct component of the transport current. And in this case, we have so-called frequency locking effect if the frequency of the transport current modulation is close enough to the frequency of the vortex nucleation. And it means that in some region of, in some interval of the transport current frequencies, the nucleation frequency is exactly equal to the modulation frequency. Also, if the frequency locking appears, we can find it experimentally just plotting an average voltage as a function of the frequency, and this is a right panel, and we can see something very similar to the plot when we consider, for example, an anomalous dispersion in optics. So using a small current modulation, we can control the vortex nucleation frequency near the resonance. Also, very interesting to restrain or to suppress chaotic behavior in the vortex motion with a small modulation. And our modeling showed that it is really possible. Using a small modulation, we can suppress a chaotic motion if the transport current frequency is large enough. However, in the chaotic, in this case, which is presented on the slide, we also have a fringe of frequencies. You can see it on the right side of the left panel, and this happens to the effect of the voltage signal beating. Okay, so what are my conclusions? First of all, vortex dynamics in open superconductor nanotubes is very rich and controllable by the magnetic field. The vortex motion in nanotubes can be studied experimentally using the induced voltage spectrum. Smaller nanotubes can find vortices in a narrower region, so there are less possibilities for chaos to emerge. The vortex nucleation frequency can be controlled with a small modulation of the transport current due to the frequency locking, and chaos in the vortex dynamics can be suppressed using the transport current modulation as well. Thank you for your attention. I can't hear you. I don't hear anything practically. well, it is very silent.
Hi.
Yes. Hi. Now it's fine. Yeah.
Hi, can you hear me?
Yes, I can hear you now.
Okay, so you hear me now properly?
Yeah, I hear you.
Great. So then there is time for questions now, so thanks for the talk.
Yep.
Anyone wants to start? So perhaps can I ask already a question? It's related to you discussed, let's say, the presence of chaos, no? So, and I think chaos is unwanted to some extent, the width dependence. But can you also comment on the length? And a question I had is, what are your boundary conditions? Are these normal metallic contacts, or is it really a superconducting boundary condition?
Well, along the nanotubes, where we have contacts, there are metal superconductor boundary conditions, and at the ends of the nanotube, there are free boundary conditions.
Okay, thank you. If I don't see questions, I can ask one more, because I had one which was not clear for me. Can you comment once more, let's say, the presence of these fractional Shapiro steps? For me, it was not clear how the bifurcation of the channels leads to fractional Shapiro steps. Can you explain that once more?
You mean these fractional harmonics?
Yeah, so here, and then you explained it like with the bifurcation, and I can understand, I see that, but how this comes back to measuring fractional steps was not clear for me.
You mean the appearance of the fractional harmonics with blue arrows? How does it related with different trajectories, right?
Yeah, because you have the same amount of vortices passing a contact. That was my confusion. Yeah, anyway, can you enlighten me?
Yeah, the process is the following. If we, for example, we had only one trajectory, and and the nucleation of the vortices generated some frequency in the induced voltage. For example, we make a little bit larger magnetic field, and in this case, we have practically the same frequency of the vortex nucleation, but one vortex chooses one path, and another vortex chooses another path, and depending on the path, it can generate different values of the voltage. So, for example, one vortex generates a smaller voltage, another vortex generates a larger vortex. And if we had, in the case of the one path, we had a usual sinusoid, for example, for simplicity, let's say they are sinusoidal signals. In the case of two paths, one period is smaller and another period is larger. So that generates a new harmonic, which is which has twice smaller frequency.
Okay, thank you for, let's say, the small extra explanation. Keeping track of time, we have to stop here, so let's thank the speaker.
Thank you.
Normally you should expect a diploma, but of course physically I cannot give that, but thank you for the talk.
Okay, thank you.
All right, can you hear me? Okay, that's good. I hear you very weakly, but I got this was affirmative. Anyway, if you can't hear me, you will stop me, no doubt. Good. So first of all, I apologize that I cannot be. Yeah.
Sorry, because the microphone was not working. Let's start again so I can introduce you.
Oh, okay. Yes.
Sorry. Let's start again. So let me welcome the last speaker of this part, let's say, which is as well from Belgium, from the University of Antwerp, Jacques Tampere. So Jacques, the floor is yours.
All right. Thank you. So yes, first of all, let me apologize for not being present in person with all of you. And I would, of course, also like to thank the organizers and especially Professor Fomin for nevertheless giving me the opportunity to present some of our work here. So I'll be shifting gears a little bit, and I will be talking not about Cooper pairs in solids, but Cooper pairs in atomic quantum gases. And I'll begin my talk by trying to explain to you why these quantum gases are good quantum simulators for nanoscopic superconductors, especially given some recent breakthroughs in confinement and manipulation of these systems. And then in the second part of my talk, I'll say a little bit about polaronic effects in these systems. And then in the end, I'll try to bring it together to tell you why I think these polarons are interesting ways to probe nanoscopic superfluidity. Good, so since perhaps not all of you are very familiar with the quantum gases, let me remind you quickly about the timeline for these systems. So on the picture on the left, you see an experimental setup, and there's a little blob in the center. That's sodium atoms that are trapped, and they can be cooled down to nanokelvin temperatures. And when they are cooled down, then they can reach a Bose-Einstein condensation, and this was first demonstrated in '95. It took a little while to show a pair condensation of fermionic atoms, because the fermions are harder to cool down, basically. But nevertheless, this was demonstrated, and then shortly after, it was shown that this pair condensate of fermionic atoms was also superfluid, and this was done by rotating the system. And if you rotate it, then you see a lattice of singly quantized vortices nucleate, and that's really the smoking gun proof for this superfluidity. So why are these things good quantum simulators? Well, basically that's because there are many parameters of the system which can be controlled to a high degree and tuned very well. Maybe the most well-known of these parameters is the interaction strength between the atoms. So you can actually bring this system in a regime where the fermions form tightly bound pairs. And then these pairs are like bosonic point particles. They will undergo Bose-Einstein condensation. And then you can tune the interaction over the unitary regime into a regime where you have weakly bound Cooper pairs and a BCS type of superfluid state. But there's more than that. You can also tune the geometry, the dimensionality of the system through this confinement. I will come to that in a minute to tell you a bit more about that. But there's many other knobs. There's, for example, the spin imbalance that you can tune, so you don't need to have an equal amount of, let's say, spin up and spin down pairing partners in these systems. And if you can think of this one as an artificial Zeeman field, maybe that you add, then you can also add spin orbit coupling to the system. And moreover, you can make the strength of this spin orbit coupling tunable. And so people have been using this to try to create exotic forms of superfluidity in this system. So if you think of the spin imbalance case, then you can try and create the FFLO state. Whereas if you add in also spin orbit coupling, you can start looking for topological superfluid states. right? But let's first turn a little bit to this confinement, because I want to tell you what's nanoscopic about these systems. And for that, I have to look at the relevant length scales of the system. That's the coherence length and the correlation length. Correlation length you can think of as the size of these pairs, and the coherence length that you can think of as the typical distance over which the pair condensate can heal or can change when you put an external potential in. And well, you see this correlation length nicely goes down as the pairs get more tightly bound. That's the red curve. But if you look at the maximum of the two, then this does not drop much below 1 in these units. And these are units determined by the Fermi wave number, which is for these systems typically on the order of inverse microns. So the effects of confinement, so when confinement will start to modify the superfluid properties, that's really on here the 10 to 100, or 1 to 10 micron scale. So it's a few orders of magnitude larger than what you have for the solid state superconductors. And in fact, most systems are already in this regime. It's kind of hard to look really at bulk type of superfluidity. But there's more. There's some recent breakthroughs in how we can trap these systems. And one is the BC on a chip. So there, in addition to the externally applied magnetic and optical trapping fields, there's also the field that comes from the circuit that's drawn on the chip, so from the leads on the chip, which influence the trapping potential. And then you can, by drawing a circuit on your chip, also make a circuit for these condensates and these gases. So here's an example by Mukuri et al., where you have both condensates that's being wound around each other, and this is being used as a detector of rotation, a very sensitive detector of rotation. And the other technology that's basically the same as you have here in the room, an overhead projector, where you have lots of digital micromirrors that you can tune, or you can achieve the same with an acousto-optic deflector. What you have is a laser beam that scans on a scale that's very faster than any other scale, and with that you can really draw potentials. And people have been making nano rings, if you wish. They are micro rings, but they are nano rings for what the condensate is concerned, nano squares, or a pearl necklace, or all sorts of other configuration that you can make. Because I knew that, or I suspected that the previous lecture would indeed be about cylinders. Here we also have a cylindrical type of confinement. Here the atoms, so it's blue detuned laser beam which repels the atoms, they're confined inside. But if you use red detuned light, then you can try to make a cylindrical confinement where the atoms go towards the edges of the cylinder. And people have been doing all sorts of funny stuff with that. So here you see a Bose-Einstein condensate that's subjected to a potential in the shape of Bose and Einstein. So indeed, lots of different ways to manipulate these condensates, both playing with the confinement as well as trying to play with the type of superfluidity that you have by adapting the parameters. So let me now go to the second part of the lecture, where I talk a bit about polarons. And well, you're probably aware of the solid state polaron, which is an electron put in an ionic or polar crystal, and it deforms the crystal lattice, and the electron together with the lattice deformation forms the polaron. So that's described by the Fröhlich Hamiltonian that you see here, with the term for the electron, a term for the bath of bosons, where the frequencies here are the LO phonon frequencies. And then there's the interaction that basically tells you that electrons can emit or absorb a phonon with a certain Fröhlich amplitude V of k, which goes like 1 over k and is proportional to a constant alpha. So the remarkable thing is that if you place an impurity atom in a Bose-Einstein condensate, that system will also be well described by a Fröhlich Hamilton, at least that we copy. So there, now the bath of bosons, you have to be careful. It's not going to be the bosonic atoms. So here, if I place a potassium impurity in a rubidium condensate, the bosons that we talk about that will dress the impurity are not the rubidium atoms. Rather, they are the excitations of the superfluid. So here there will be the Bogolyubov excitations of your superfluid. So you have to replace the typical frequency of these guys by the Bogolyubov frequency. You see it starts as a sound mode with velocity c, and then around the inverse healing length, it turns over more particle-like. Note that the interaction strength here is no longer going down as 1 over k, but for large k, it's going to a constant, and so that will need some renormalization. So we've been extensively studying this system from 2009 till 2013 with the last publication in 2015. And this is mainly the work that was done in collaboration with my PhD student at the time, Wim Casteels. So if you want to know more details about that, you can don't have to download the individual papers. You can simply download his thesis. It's very well nicely written up in there. So 2015, it took, there were no experiments then. The first experiments came in 2016 by a group of Debijin in Gila and Jan Arlt in Aarhus University. So how did they do that? They started, so this will be the experiment of Arlt. They started with a Bose condensate of potassium-39 atoms in a state that we label state 1. And then with a radio frequent pulse, they are going to do a spin flip and flip this to another state, the M0 state, here indicated by 2. And normally you have to pay the Zeeman energy for that. But if these impurity atoms form polarons, so if they start to dress themselves with the excitations of the superfluid, then the energy will be shifted by the typical polaronic energy shift. And this energy shift is something that you can measure, or at least that they attempted to measure. You see, the green wiggly line doesn't all the way go down to 0, it goes to some curve here. So I'm going to be focusing on what happens to the right-hand side on the repulsive polaron rather than on the stuff on the left-hand side. So here you see the experimental results. It's a little bit messy, but you can see the trend. And so if we put some theory there, then that's shown here on the right. So the diamonds are diffusion Monte Carlo calculations by Luis Pena Ardila. There's some other curves there that are variational Monte Carlo things, and the circles are the experiment. See, the experiment is a little bit messy. There's different ways to extract this data and get the energy shift. There seems to be a systematic shift upwards there. But the bad news for us was that, well, this black curve here was our theory. So it's nice, it matches nicely when there's a weak coupling, so on the right-hand side of the part, but then it comes kind of crashing down. And since we very much like the Polarons and Feynman's approach, we tried to figure out what was wrong and had to do several corrections. First of all, when you get to stronger coupling, now you have to add new terms to the Hamiltonian beyond Fröhlich terms, which involve an electron that interacts with 2 of these Bogolyubov excitations. And then that didn't turn to be enough. We also had to improve the approach that was developed by Feynman for the original solid state polaron. And the main improvement here was to generalize the memory kernel. So in Feynman's model, you represent the phonons by a mass attached by a spring to the impurity. And this gives you a retardation interaction between the impurities that's dominated by a single frequency. So what we had to do is generalize this to this memory function, memory kernel X And rather than having M and W, two variational parameters, we now had to do a functional minimization with respect to the memory X. That work was done by another PhD student, Timur Ikhmukhamedov, and also led to a series of papers, which in the end became his PhD thesis. So let me show you the results now, and it's already looking much better. So the diamonds are still this Monte Carlo results that we wanted to get closer to. The blue line here is a renormalization group developed by Grust, and this is also Daimler and co-workers. Mean field is like a Lilo Pines thing that we know is going to fail at stronger coupling. So that's nice. And if I superpose or try to superpose on this the experimental data, you see that the trends are there. But still, as we know from before, this experimental results are a little bit above the Monte Carlo data, which you can see even at rather weak coupling, so upper right-hand part. And since Monte Carlo is supposed to be exact, there must be something that is not taken into account there. We thought about it, and our suggestion for that is that it's an interaction shift, because there's really a very high density of impurities. They don't just make one impurity in the Bose-Einstein condensate, but they put a lot of these impurities there. And so you can have things like bipolaron formation, tripolaron, or in interaction, many polaron physics. And indeed, if you would look at the bipolaron problem now, this is the red dashed line here, it seems to lie much better with these experimental points. But this is this is preliminary. We still have to refine this part, but we do think it's due to the interaction part. Okay, so now I told you about these interesting superfluids and about the polarons. So I want to bring them together with something that we now plan to do. And that's bring these polarons from impurity in a condensate towards impurities in superfluids, exotic superfluids, and confined superfluids. So we started out, if you wish, on the right-hand side here, on the BC side, where this red line, the Bogoliubov spectrum, is the main fluctuation present, and the impurity interacts with that. Now we want to bring it to the BCS side, where there's a lot more fluctuation. So this Bogoliubov mode is influenced by a pair breaking continuum that will be there. There is a Higgs mode on this side. And there's people have been looking at these modes, as you can see, with a lot of different work, both in experiment and theory. There's one particular work that I would like to draw your attention to, and that's our work, which will be presented by Sergei Klimin at this conference later this afternoon at 17:40. So we also calculated this kind of spectral functions, in which we can find that there's lots of different modes that will start to address the impurity. And so the idea is, of course, to look also at this, at whether we can use the impurity to see these kind of modes and to determine what superfluid phase we are in. So this is going to be a part of the work of a current PhD student, Laura van den Bremen, whose work it is to go from the BC polaron on the right-hand side of this graph at the bottom, more towards the left to the BCS polaron. And then I also want to draw your attention that these impurities can be subjected to their own confinement potential. So they can be localized within any other shape that you are going to create for these superfluids. And they can be a local probe of the excitations of the superfluid, and hence of things like the pair density, etc., etc. Good, I think I've used up my time, so I will finish there, and thank you for your attention.
Okay, thank you, Jacques. I hope you hear me.
I can hear you.
Okay, great. That's already a plus. It's time for questions. So the floor is. Yeah, so if, let's say, then I can take the word, I can ask a question. So,
Sure.
Jacques, the first question, let's say, which for me was, because you say the tunability of this type of, I mean, I'm completely out of this topic, let's say, from experimental point of view, but how, can you comment, how do they induce the spin-orbit interaction, how this is done?
This is done basically by coupling the atoms to a laser field, which will impart a momentum spin dependently. So the laser field gets, so you absorb from, it's actually a Bragg scattering kind of thing. So you absorb from one laser beam to the other laser beam, but the beam couples it couples differently to the different spin species. So basically your spin up atoms get a kick to the left and your spin down atoms get a kick to the right. And if you go back to the spin orbit coupling thing, and then you can see the dashed blue and the dashed red line are basically these kicks that you can give.
Okay,
and then because they interact, you get effectively, if you write down now the single particle Hamiltonian, you will get a spin orbit coupling.
Okay, then perhaps let's say also a final question, because we also have to take the coffee break, but is related to, I mean, making the potential on the one which was on your conclusion slide, which is the fast laser scanning. So, so which is or here at the right, all these beautiful, let's say, what is the time scale you need to do that? And actually, can you really say then, I mean, that this is a uniform potential, or the dynamics is important, and can they even play with the dynamics?
So you can play with the dynamics, but you can draw much faster than that these condensates can respond. So the speed of sound is let's say what you would have to look at, and this is rather slow. So it's on the order of, so from on a micron scale, it's milliseconds. And so you can make these devices that will draw much faster than milliseconds. Right, your screen is updating. A good screen is updating at 100 hertz, so once every 10 milliseconds, and that's usually a much more complicated pattern to draw. So yes, that's what we can do. Let's say the kind of more limiting thing is how finely they can focus it. So you have to be able to focus the thing also smaller than these two length scales that I showed you, these two guys, right? And so that's kind of on the edge. So the edges of our potentials, we can try to make them sharp, but we will not make them completely sharp. And maybe I forgot to mention one of the most important things, but it's rather fresh news. So we work together with University of Ghent with a group of Karel van Akkoleijen, who now have, since a few weeks, we have our first BC on a chip, which we will be able to combine with this acousto-optic deflector method to draw potentials on these things. So we're looking forward to doing that. So we just have reported, let's say, the realization of Bose-Einstein condensation in the TAP, which is the first step, cooling down the atoms to making them cool enough to see this PC.
Okay, thank you, Jacques. So let's thank the speaker and also all the speakers of the session.
Thank you, and goodbye, everyone.
Yeah, so it's my pleasure to express to all speakers of our session very cordial thanks for their great contribution, very nice and elucidating presentations from various directions, which nevertheless made clear-cut picture of the present state and perspectives of 3D superconductivity and related topics. Thank you very much, and much success in the continuation of your scientific work. Here the session is closed.
Yes, yes, now I can hear you.
Okay, fine.
Can you hear me?
Yeah.
Okay.
Okay, so let's
I
start.
share my screen. I hope it's appear for you.
Okay, so let's start with this session, the last session of the day. So the first speaker is Doa Subi from Budapest University of Technology and Economics, and she will talk about using quantum nodes connected via the quantum cloud to perform IoT quantum network. So please, let's start.
Hello, good evening. I would like to apologize because I can't attend in person, and thank you for the conference organizers that understand my case. So I need to present online. My presentation will be talk about the using a quantum node connected via a quantum cloud to perform IoT quantum network. And let's start with our main topics, which is talk at the first about the quantum communication principle, quantum communication limitations, solution and possibilities, and related work, and our suggested model about the quantum nodes connected via cloud to the quantum computer, which will work as server. Let's start with the comparison between the classical and the quantum computers. Classical computers, as we all know, that it is used the binary bit, which is must be on, that represent the logic 1, or off, that represented by logic 0, and this is a series of these binary bit will represent the information that used to in the classical computer. While in the quantum computers, we are using something that completely different, which is called the qubits. These qubits have a special properties. First property is superposition, that meaning that the quantum computer could represent the state at 1 and 0 on the same time, and this will give a high power for the quantum computer. And the second thing, important property, which is used and give the power for the quantum information, which is the entanglement. Entanglement actually is work such as a magic connection between two qubits, if even if they are distinct and travel for long distances. According to the above, the superposition property giving the power to the quantum computer because it is the basic for the quantum register. Let's explain. If we have one qubit, we will represent two states on the same time. If we have two qubits, we can represent four qubits on the same time. If we have three qubits, we will can represent 8 states on the same time, and so on. This is which gives the power for the quantum computer over the classical one, and which make it more useful if we use it on the data center, on the servers, instead of or integrated with the classical computer. But there is still many limitations for use of the quantum system. We say previously that we have entanglement and superposition for the quantum bits, but here these quantum bit properties are fragile and attenuated if they are travel for the long distances, and there is a loss of coherence between these two qubits. Decoherence is the losses of the coherence, and the coherence which give the qubit the power of superposition. Due to this decoherence, the qubits are extremely fragile, so that their ability to stay in superposition and entangled state is attenuated. Another limitation, which is represent power and limitation on the same time is no cloning theorem. The no cloning theorem meaning that the state is impossible to create an independent and identical copy of an arbitrary unknown state. It is represent the power in the side that our information cannot be stolen by eavesdroppers, and on the same time we cannot transmit the information for long distances because we cannot use a repeater to copy and forwarded it. But there is a solution. Bryagel and Dorr on the late of 19th century decade suggests a new quantum repeater that will work on the has the similar job of the classical one, which is transmit the information for long distances, but its principle of work is different completely. Quantum repeaters are based on two quantum principles, which is entanglement swapping and Bell-Bear. And based on these two properties, he will solve the coherence, attenuation, and qubit fragility. And the quantum Bell-Bears generated between two neighboring repeaters, and entanglement swapping will connect the distance repeaters with each other by connecting their Bell pairs, and at the end we can connect two distance nodes by using quantum repeaters. Related work, actually there is very too much novelties and contribution in the field of quantum information, but here we will illustrate only something that are related to my work and suggestion. First, we talk about the quantum repeaters type. Actually, at the 2016, I'm sorry, Jonas suggest three types of quantum repeater node. First one is called meet in the middle, which is contain this BSA. BSA is abbreviation for Bell State Analyzer. This Bell state put in the between two quantum nodes. Both quantum node will send photon, and this BSA will create entanglement and share for the both these nodes. The problem with this BSA is situation due to geographical area, and it must be there is a synchronization between sender and the receiver, and it must know the number burst time, buffer size, and others. It has many advantage and disadvantage, and it is used according to the situation. The second one is sender receiver type, which is have only built on BSA node, which is put it in the receiver. The sender will send the photon, and on BSA create the entangled pair and share it to the sender. The third one, which is midpoint source, in this type needed for the entangled photon pair source, EBS, in the middle, and each node must have a BSA node. This node in the middle will create the entangled photon and share for both sender and receiver. In our work, we will use the first one. Second related work is the second novelty is for Delberg and his group, her group from Netherlands. They are suggested a link layer protocol and simulated. This is by using a few qubits executed on supercomputer. The third suggestion, which is the third contribution is for Takako Matasio from Japan, who is suggest a rule set that coordinates the operation of a quantum network over both link layer and network layer. Based on all the above, we suggest our model. We connect, so just connecting different nodes via a classical channel and a quantum channel to a quantum computer. This quantum computer will work as a server or database, such as this computer connected to multi things. This quantum computer could process storage, work as processor, storage memory. This has different advantages. One of these advantages is to save information securely, as we know, because most important use for the quantum communication is the security and the high power processing. This quantum computer could work separately or integrated with a classical computer to connect these terminal nodes via cloud to it to collect information, process it, and forward it to the connected node via a classical channel. The processing will work as in details here. A quantum node activated classically by sending a boot-up notification to the BSA node. BSA node we explained in the previous section. And BSA node will calculate the photon emission time per stride for all neighboring quantum node and photon detector for recovery time. This BSA forwarded this information classically for all neighboring nodes to generate entanglement. At the end, the quantum node notified BSA node classically that he is the work was success or failure, and then the BSA node will close the communication and notify for a new round trip time. This is the BSA node, which is put in the middle between two quantum nodes, or which is sender and receiver. The receiver in our case is a database. The point in the middle will create entangled pair and share for both nodes. Then after the shared entangled pair sent, the sender sent its information to the receiver, and on the receiver side, the quantum computer receives the information, process it, and return the instruction. When the sender received the instruction, sent a new request to establish a new communication. This is in the future will be applied using a simulation thanks to Takaki Matasio, who is built a QISV a quantum simulation package on the ONNET++, which will be able us to build a quantum network without need to the real quantum computer and calculate the fidelity of the network and other quantum properties. Thank you for your listening.
Okay, so thank you for the presentation. We have time for questions or comments. Okay. So it seems there are no questions, so let's thank the speaker.
Thank you very much for your listening, and goodbye.
And let's move to the next speaker. Is Ilmaz Simsek from Sabancı University Nanotechnology and Application Center. And it will talk about transport characteristics of coplanar niobium iron oxide niobium Josephson junctions.
Oh, it doesn't work. This also doesn't work. Ah. Yeah, it's working now. Let me go. Oh, okay. Yeah, it's working. And laser is not working, but I don't know. Ah, this guy. Okay. Thank you for nice introduction. And today I'm going to talk to the characteristic of this coplanar Josephson junction. Oh, me? Yeah, it's working. Yeah, this is the new Josephson junction and with the magnetite tunneling barrier. And actually we expect to see the pi junction characteristic in this, from this Josephson junction. And actually this is the ongoing project. We started 1.5 years ago. And today I'm going to show the synthesis and also characterization of these all films and also the electric characterization of this Josephson junction. Okay, let me start with my motivation. Actually, recently we worked on this superconductor, which is the iron arsenic superconductor. And we substituted this rubidium with the europhonium, and we observed that this guy shows some magnetic behavior in this direction, and another magnetic layer here, and this is another magnetic layer in this direction. This is the really nice Josephson junction, but unfortunately this one doesn't show the Josephson junction behavior. And if you look this is the a specific heat capacitance, and there's two peaks. One is corresponding to superconductivity, the other one is corresponding to this magnetism. But these are, and if you look, this is the antiferromagnetic. It's not antiferromagnetic, but this line shows this and this oriented to this one, and total magnetic magnetization is 0. And now okay, these are we just measure it, and this is our motivation. Let me just start give the brief introduction about the ferromagnetic junction. And we just this one is if you put to the superconductor the ferromagnetic layer between the two superconductor, and it gives you the more physics. And these are the odd frequency pairing and FFLO pairing and pi junction characteristic, long range, equal spin current, and also the proximity effect. And this one is actually very useful to modify for the quantum computing, to modify for phase shift of the qubit. The other one is the presence of the spin triplet supercurrent, as it's really useful for superconducting spintronic applications. And I think our purpose is, first of all, we want to just design this one, and these are our pi junction to control the qubit structure, and like this one is behave as a phase shifter, and then we want to modify this phase shift by applying magnetic field. Okay, and actually in the literature, and if you increase the voltage jump, and they put the insulating layer, but this one, and there is some quasi-particle excitation because of this metallic layer. And then also we want to increase the junction voltage, and how we can put the ferromagnetic insulator between the two superconducting layers. And these are just the tick, and we want to just look to the signature of the pi junction, and these are just the thickness-induced 0 and pi junction transition, and cost structure in the temperature depends on the critical current, Fraunhofer pattern, or also change in the Rn product. And these are just the application and spintronic and also the superconducting qubit. Actually, our purpose is go towards the superconducting qubit applications. And actually, I want to summarize it today in the morning section, and you also briefly summarize it. Our purpose to get the ferromagnetic insulating layer between the two superconductors and to observe the pi junction characteristic. First of all, we want to see the cusp structure, and in the as a function of the barrier thickness. And the other one is also the cusp structure and critical current change as a function of the temperature. The other one, the Fraunhofer patterns. And this one is actually is well-known effect if this is the proximity effect. And if you increase the thickness of the magnetic layer and the superconductivity suppressed, and these are I also put this plot here. And these are the magnetic insulator, and people always is working these ferromagnetic insulator, but we prefer to form the magnetite structure in the between the structure. This one is very promising candidate, and for spintronic application, and these are the high unique electrical characterization, also magnetic properties, high Curie temperature, and high spin polarization. And it also shows us the very transition around 120 Kelvin. This is a structural phase transition, gives to you some kind of the phase transition from the semi-metal to insulating phase. And these are just how to grow our films, and we use the AGA sputtering system in the Boğaziçi University, and these are the magnetic stages to focus the plasma towards this stage. And these are, you can see the TM picture of our junction stack, and these are our junction is around here. And also we looked at the topology of the niobium, and also the iron oxide layer on the top of the niobium. And it's really the roughness is less than the 1 nanometer. And these are just the Sunum facility at Sabancı University, and we can fabricate the nano scale size devices, also microwave devices, and also the wafer size devices you can see. And we have two cryogenic system. One is the Teslatron, and the other one is the dilution fridges. And one is we can also go to the up to the 1.5 Kelvin, and we can apply the 8 Tesla, and this one is more useful, and we can go to down to the 10 millikelvin, and also we can apply the 12 the Tesla magnetic field. And we also have this one, but we couldn't implement this device, but it's really ready, and this is we can do the angular dependence of the magnetoresistance resistance measurement by this. And you can see our sample design. One is that we can use the top to bottom fabrication method, and why we prefer this one I will tell you. And today I'm going to talk show the electrical measurement of the coplanar Josephson junction, and we fabricated by EBL structure. And actually, I want to talk. Okay, we are starting at the beginning, and right now we have to solve some problem. One problem is the niobium oxide on the niobium, and you can see the niobium pentoxide or niobium dioxide is also present on the top, and also you can see that this oxide structure at the top of the niobium, and this is the reason why we use the cap layer. And these are just the niobium films, and we just grow on the MgO and sapphire substrate, and with the different power, and also we just optimize the sputtering condition to get the really superconducting films. Actually, and it's really grow on the MgO substrate, and it gives the high TC superconducting state. And actually, there's some problem. Maybe there's some, but definitely I can just show you here, and you can see that the boundaries of this upper critical current on this is the niobium on the sapphire, this is the niobium on the MgO substrate, and this critical, the upper critical value is around 7.7 Tesla, and on the niobium, for niobium on the MgO substrate. Okay, now we need to also optimize the spotting condition to get the exactly true magnetite crystalline structure on the niobium. First, we just grow it on the MgO substrate to how to, actually our purpose is epitaxial Josephson junction. First of all, we want to get the epitaxy film, and it's easy to put to some kind of the epitaxial film or crystalline structure. And then we can also put another one is like this. And our purpose is to get the crystalline form of the iron oxide layer, which should be magnetite. And we need, this one is help us to avoid the disorder bonds, also defect in the tunneling barrier. This is very important for the coherence. And actually, we found some parameter, and I don't want to go to the details of the XPS result. And simply, I can say that this ratio between the iron 3 and iron +2 ions, this ratio is very close to the literature value, and it tells us the purity of the magnetite phase, but the XRD is telling the different. If you look at the XRD, and we have a magnetite and hematite phase present in our structure. And you can see the transport characteristic of the coplanar junction is the coplanar junction, and TC shows the 2 steps, and most probably upper end, the lower films shows the different superconductivity. And this, you can see the IV characteristic of this junction, and also we looked at the temperature dependence of the critical current density. Actually, it shows the Amberkar-Baratov relation. Somehow there is some little bit cusp. We are not sure. We have to be, because thickness should be very important for this guy has a 6 nanometer the iron oxide layer. I am not telling that this is the magnetite, but definitely this is the iron oxide layer. And you can also, this is the Fraunhofer pattern of this structure, and you can see here this is the IV characteristic of the coplanar junction under the magnetic field. Magnetic field is applied in this direction. Actually, this was we couldn't expect some Fraunhofer pattern because we apply the magnetic field in this direction, not parallel to the tunneling barrier. And then we observed some kind of the Fraunhofer-like pattern-like behavior, and it shows like this. But in your talk, and there's this peak is shift to the negative side, as I remember, and ours is like this. And of course, we also repeat it, and we are really getting this kind of the Fraunhofer pattern. Most probably, let me go back this shape, and yeah, maybe, and this one is this part is upper part of the niobium. That means that this guy is covered like this, and we have a Josephson junction in this side, here, and at the later size of this film. And maybe this one is really parallel to the magnetic field, and then we got this Fraunhofer pattern. We don't know. Actually, this is not my design. They changed this design accidentally. We got it, and now this is the last result, and this is the Fraunhofer pattern of one of the mesa array. It is around the 500 nanometer size, and these are IV characteristic of this one. Unfortunately, and we always is getting this kind the lower TC, and we try to figure out why the TC is decreasing. Maybe this is the over edge of this structure, or magnetite is decreased. The magnetite layer is decreased the TC, and we don't know what exactly. This is the Fraunhofer pattern or critical current, how they oscillate with the magnetic field. And we apply the magnetic field and it's perpendicular to this surface. And then we got again the same and some kind of the Fraunhofer pattern, but we are not sure. We are open to discuss. We will be happy to discuss it. And this is my summary. And okay, we optimize all conditions to get this pi junction structure characteristic, and we just still going on and optimization of the deposition condition to get the true magnetite structure also. This is our future work, and we want to just grow the series of the Josephson junction and with gradually varying the thickness of the iron oxide layer, and to look at this signature of the pi junction characteristic. Thank you very much. By the way, these are my group, and we are in, and we just I just showed the result of today, and also we are growing the high tissue superconducting films and 4 terahertz emission. Thank you very much.
Okay, so we have time for questions, comments. Yes, please.
Thank you for the interesting talk. I have a question. Did you have any evidence that the barrier is magnetic?
Yeah, actually we just looked at the XRD result. It's a magnetic, and we also looked at the VSM, but we couldn't detect the weak signal. And right now is we try to understand, okay, electrical measurement maybe give us the signature of this behavior. And of course, it needs some kind of the advanced analyzing for like the squid maybe. It's maybe useful. And VSM cannot give us this transition or magnetic behavior. Definitely. I'm sorry. VSM tell us okay, it's a magnetic layer, and but we couldn't observe this wave transition. Wave transition, very special case for magnetite.
Okay. And how about the conducting state? Do you have evidence whether it is insulating or metallic?
It shows the metallic. Somehow, because I'm just looking to this, the voltage jump is what I expect. I expect the really millivolt range, but it gives the nanovolt, something like this. Thank you.
Yeah, sure.
Thank you for the nice presentation. Is there a reason why you choose MgO as a substrate?
Actually, we try to optimize the parameter on the different subsets, silicon and sapphire and MgO. And in the literature tell us, okay, it's really growing very well on the MgO. And also magnetite can also grow well on the MgO substrate. And we looked, okay, TC is really high. It's close to 9 Kelvin. And also it shows some crystalline structure, and then it's okay for us. And for silicon, and we just observed that the TC is down to 6 Kelvin. I don't know, maybe because of our deposition condition. I'm not sure.
Okay, just in the for the thin film.
Yes, for the thin film to get it.
How thick was the film?
Film
150.
150 on one layer. And second layer is also 150, and we have an iron oxide layer.
Okay, thank you.
Thank you very much. Is there any other question? So if not, let's thank the speaker again, and I'm glad to give you this certificate.
Thank you very much.
And so there are no more speakers, and the session is closed. Okay. So see you.